Okay, let's start.
Okay,
right.
everybody, good morning, and thank the organizers for this excellent conference, and I've been following it and enjoying it. I wanted to make a quick announcement for the conference. If you go to the front page of the website of the BBC News this morning, it features the paper by Javier Calme and Roberto Casadio on black holes having her, and they've announced it. And this is not a physics journal at all, but they've announced it and they've highlighted it, and I think that's very nice because those are things that these are things that they've been here and they've been talking about at this conference, and so this is I think very nice for all of us. Okay, now I'd like to talk about my own work. How to quantize gravity and how to not quantize gravity. And I'm going to say things which I think might be somewhat provocative. Now, quantum electrodynamics is the paradigm that we have for quantum field theory. Think of the Maxwell equations. They're really quite remarkable. They were written down by Maxwell in the 1850s. They've remained intact following special relativity in 1905, general relativity in 1915, and then quantum field theory in the late 1940s. They never had to change. Originally written down by Maxwell and Gauss and Ampere and Faraday. These are the standard Maxwell equations, and you can write them in special relativistic form immediately so that they already obey special relativity. With general relativity, you just replace ordinary derivatives by covariant derivatives, and the equations are basically the same. Nothing gets changed. When you quantize the theory, the only thing that you do that's different is you interpret the fields as Q number operators that have non-trivial H-bar dependent commutators. But the fact that the Maxwell equations do not get modified in form is because quantum electrodynamics is a renormalizable field theory. Matrix elements of the quantum operators in states with an indefinite number of the photons obey the classical Maxwell field equations with renormalized parameters. So you really get classical from quantum. This limit is not a limit in which we set H bar to 0. H bar never is 0 in the real world. It's always non-zero. Instead, it's a macroscopic limit in which interference effects cause H bar dependent terms to mutually cancel each other, and the center of a wave packet follows the classical trajectory. That's Ehrenfest's theorem. So this is how we get to classical physics. Now, in the Feynman path integral, you make a stationary phase approximation, and you replace the integral by just one path, the stationary classical path, which is a solution to the classical equations. So what happened to all the other paths? The other paths interfered with each other. However, while the solution doesn't depend on H bar, the phase of the path integral action in the solution does depend on H bar. It doesn't go away. And I'm going to show you in a moment that this phase has actually been measured by the Colella, Overhauser, and Werner experiment. Next, classical electrodynamics follows from quantum electrodynamics and not the other way around. There's no separate classical electrodynamics and separate quantum electrodynamics. Quantum electrodynamics is output to an underlying quantum electrodynamic theory. Let's just think about the double slit experiment. We produce the wave, there are two slits, and then we see an interference pattern on a screen, and there you can see all the nice maxima and minima. And we teach this in introductory physics as a classical, using classical equations. However, if you start reducing the intensity of the beam down to single photons at a time, each photon will land at one point on the screen, but statistically, you'll find that large numbers of them land in one site, large numbers of them land in another site where there are the maxima, and very few of them land where there's the minimum. But because you send out large numbers of photons, it looks like you have a classical pattern. So the classical pattern is statistical. It's not a different dynamics. It's a consequence of the underlying quantum dynamics of the photons. And we can see this much more clearly when we use a neutron beam or an electron beam. So that's what we look for in electrodynamics. Now, quantum theory was not developed this way. It was developed by replacing classical Poisson brackets by quantum commutators, and we call this canonical commutation, quantization. But this is doing things backwards. Classical follows from quantum, not the other way around. The task of quantizing gravity is to find a sensible microscopic quantum theory, with classical gravity being its many graviton microscopic limit. Not necessarily, and I'll come back to this over and over, it doesn't have to be Einstein classical gravity. You have to, first of all, find a sensible microscopic theory. Now, you'd like the quantum theory and the classical theory to have the same form of the equations of motion, just like electrodynamics. Now, if you wanted to do that, the quantum theory would have to be renormalizable, and I'll talk about conformal gravity shortly as a renormalizable theory. And I've been pointing out, and my colleague, a good friend John Donahue, have always said, if quantum field theory and SU3 cross SU2 cross U1 had been developed first, rather than general relativity, people would have gone automatically to a renormalizable quantum theory. Next. So we want to quantize gravity, replicating the treatment in quantum electrodynamics. It will work, but there's going to be a surprise. Gravity cannot be quantized on its own. It's going to be quantized by its coupling to quantized matter, with there being no h bar to the zero term at all. And we should expand as a power series in h bar and not as a power series in the gravitational coupling constant. In other words, if you start with the quantum theory, then you never get an h bar to the zero term. You only get an h bar to the zero term because you start with the classical theory and try to quantize it by Poisson brackets. We'll see that very important point will be the 0 point energy, and this will be central to solving the cosmological constant problem. So what are we looking for? We're looking for a path integral description of gravity, integral over g mu nu e to the I grav h bar, which, apart from describing data, which actually exists. It has to have an appropriate choice of the gravitational action, and it has to have an appropriate domain for the path integral measure. If you can find such a quantity, which is good to all orders in perturbation theory and makes sense, you have a consistent theory of quantum gravity. Now, this procedure does not work for Einstein gravity, and so one has to apply what you might call radical surgery to quantum field theory and pursue a different approach, such as string theory or loop quantum gravity. It does work for conformal gravity, and it is renormalizable. It's got a dimensionless coupling constant. Its ghost unitarity problem has been resolved by myself and Carl Bender, and I'll mention that a little bit later. And the interesting thing is that the way the theory works is the domain for the path integral measure has to be continued into the complex plane. And if you don't do that, the path integral doesn't exist. And that's a step which is not usually taken in analyzing path integral approaches to gravity. Our new contribution, well, it's not new now, but the key step is going to be finding the right domain in the complex plane for which this integral actually exists. But before we do that, let's ask a very primitive question. Does gravity actually know about quantum mechanics? Before we quantize it, we better discuss whether we need to. Now, macroscopically, there are two established sources of gravity that are intrinsically quantum mechanical. The Pauli pressure of white dwarf stars with Chandrasekhar mass, which explicitly depends on h bar, and then the energy density and pressure of the cosmic microwave background blackbody radiation in cosmology, which also depends on h bar. So two phenomena, blackbody radiation and Pauli degeneracy of white dwarfs, are well established macroscopically And this is quantum mechanics. This is quantum mechanics on large scales. What about microscopically? There was an experiment done by Colella, Overhauser, and Werner. And what they showed was they took basically an interferometer in the vertical, and they sent light rays or neutrons around it, and they observed a change in the action of the form mgh squared over v h bar, where h is the height, v is the velocity of the neutron, and m is the mass of the neutron. And they actually saw a fringe shift because this level here is at a different gravitational potential than this one. And that changes the phase. Now, you might think that a neutron going through a few centimeters would be negligible. It is, but not compared with Planck's constant. And so they actually see about 50 fringes. Now, beyond that, you actually get a bonus, and that is that they measure the phase. And the phase is the classical action times 1 over h bar. And so they measure the classical action. And this is not done in classical physics. Now, it's very interesting. The trajectory that the neutron follows does not depend on its mass. That's the classical equivalence principle. The quantum equivalence principle is the statement not that the masses are equal, but that the de Broglie wavelengths for gravitational and inertial scattering, Mi and Mg, that they are equal, namely interference in the horizontal is the same as interference in the vertical. And that's the quantum mechanical version of the equivalence principle. Theoretical considerations. We write the Einstein equations, 1 over 8 pi g, r u nu, and so on. If the Einstein tensor is equal to the matter field energy momentum tensor, and that says equals, either both sides are classical or both sides are quantum mechanical. There can't be anything else. Now, could gravity be classical and matter be quantum mechanical? No, because then you'd have a classical equals a quantum mechanical, and that can't be. So if gravity, we know that the source of gravity is quantum mechanical, and I just showed you, and not only that, we know that gravity knows it. Therefore, gravity must be quantized. So that's our conclusion. Now let's stay with the Einstein equations, and we should run into a problem. Gravitational experiments that I've described didn't involve graviton loops. So what we've been doing is to use a hybrid in which we keep the gravity classical, but replace the quantum mechanical energy momentum tensor by its expectation value. But this expectation value is products of fields at the same point. That's the 0-point energy density. And we subtract that off because this side has to be finite. And we finish up with this equation, 2.3. So this is the form in which standard applications of gravity are made. Now, what are we doing? If you quantize an oscillator, you have A dagger A plus a half h bar omega. You keep the A dagger A, but you throw away the half h bar omega. When we do the Pauli degeneracy of the white dwarf, we don't count the 0-point energy. We don't. And we ignore, if this is a tensor, we ignore the 0-point pressure. So those things are thrown out before we start. Now, I don't know of any justification for using this expression, but I do know that it's wrong. And the reason that it's wrong is the whole point of Einstein gravity is that gravity couples to everything. Therefore, gravity must couple to the 0-point. And if we throw away the 0-point contributions, we've not only violated Einstein's principle, but we've also thrown away where the zero of energy is. And the cosmological constant problem is trying to make sense of the finite piece with no longer having the ability to know where the zero of energy was in the first place. So I don't believe that this equation holds in the real world, and efforts to make sense of it have led us to this great problem. And even if we were to solve the cosmological constant for this equation, you still have the question, well, what happens when you do the gravitational quantum fluctuations on the gravity side. You still have to do that anyway. Okay. So, there are two types of cosmological constant problem. There's the 0-point energy that we've just described, and then when you change the vacuum as the universe cools down, we induce a huge lambda. So we really have to deal with two problems, the 0-point and the cosmological constant problem. And if we take gravity to be quantum mechanical, as we must, it too will have 0-point contributions, and those are the things that are going to save us. Now, in fact, what I've shown in my talk is, one second, Shravan, is that gravity 0-point and the matter field 0-point solve each other in a way that leads to a solution to the cosmological constant problem. And I'll get that to it in a moment, and I'll show you that the way that this works, how do they know how to quantize, cancel each other, is the quantization cannot be done canonically. Gravity is being quantized simply by being coupled to a source that is quantized instead of being quantized on its own. Okay, Shravan, you had a question.
Sorry to ask you the question in the middle of your talk, but I just don't understand what you're saying. So are you saying that semi-classical approach is wrong?
No, I'm saying that you've never shown that a semi-classical approach is right. Semi-classical works for quantum electrodynamics because we can derive it starting from quantum field theory. Semi-classical Einstein, this is just an imaginary equation that's been written down that everybody uses. The hope is that if you had a successful quantum theory, that it would lead you to this later. That's it, still a hope, but it's never been done. I mean, as far as I know, it's never been done. That's all I'm saying. I know people who say, excuse me?
No. There must be some energy scale where this is still should be valid, right?
No, I'm not saying that. I'm not saying that this should be valid. I'm saying that if you think it's valid, you better prove it. That's all I'm saying.
Okay.
It's not my job to prove it. It's the people that use it who have the job to prove it. Now, of course, if you there's no question that what is called the quantum gravity problem is the hope that you can eventually derive this equation. I mean, that's the quantum gravity program. That's the objective. And I'm saying that this is the wrong objective. That's the point. That's my point. Okay. Now, thank you. Let me do fermion fields. Very quickly, quantization. You're all familiar with it. You write down the action, vary with respect to the field, and then you quantize the field of psi dagger by introducing a canonical anticommutator. And the creation and annihilation operators obey the standard delta functions. That's canonical quantization using the field equation. Now you go and you calculate the expectation value of the energy momentum tensor of this same theory, IH bar, gamma mu d mu psi, in the vacuum that you just constructed, that the B and the D annihilate. And you find that it's infinite. Of course, it's the infinite 0-point. But you also find that there's an infinite 0-point energy, T00, and an infinite 0-point pressure, but the pressure is 1/3 of the density, so rho and P have the same sign, and therefore this is not a cosmological constant. For a cosmological constant, the pressure would have to be equal to minus the density, and that's not the case here. And these are infinite, and that's the 0-point, and ordinarily you just normal order them away. But you can't normal them away when you couple to gravity. But we'll see that in a moment. However, the fact that this is infinite doesn't make any difference because the field equations are not the equations involving the energy momentum tensor. So they're distinct. So you can live with this infinity, at least in flat space physics. Now, let's now see what happens with gravity. Does the same canonical prescription work? So I take a gravitational action, I vary it, I get an energy momentum tensor, and Weinberg in his book and myself in one of my papers have said we should treat this as the energy momentum tensor of gravity. For the Einstein theory, for instance, this is the Einstein Hilbert action, and this would therefore be T mu gravity. Now, the equation of motion is simply that T mu gravity is 0. So let's expand G mu nu is eta plus h. And then we would find the first order solution for h gives us a wave equation. In the harmonic gauge, this is box h mu nu equals 0, if we just expand around flat space-time. So that's how we construct gravitational perturbations in this view. Now let's go and look at the second order term, T mu grav, and now this is going to be the vacuum expectation value of the energy momentum tensor, and that's going to have a 0-point infinity. The very act of quantizing it means that just like with the fermion, you've got an infinite number of modes, and therefore you get an infinity in the 0 point. Now, the problem that you have is that means that the second order T mu grav is not 0. But the way that the equation that we're trying to solve, the variational calculation, oh, sorry, I've gone the wrong way. The variational calculation that we're trying to solve is that the energy momentum tensor be 0. So where we finish up with is we find that we want it simultaneously to be 0 and to be infinite, because the 0 point is the equation of motion. Now, can we ignore this? Well, of course we can't, because T mu nu grav 2 is the energy carried by a gravity wave. So we have to have, this has to be non-zero. So we run into a problem with gravity. Gravity can't be quantized canonically because the 0 point can no longer be ignored. Namely, gravity couples to gravity, and therefore gravity sees its own 0 point energy, and you can't pretend that it didn't. So what are we going to do? So we have to do more. We have to introduce a source at the same time. We'll take I gravity plus I matter, and then the energy momentum tensor of the universe is going to be the gravitational piece plus the matter piece. And as long as this is a well-defined quantum mechanical equation, then we can treat T mu nu universe equals 0 as a quantum mechanical operator identity. And then it's going to have finite pieces and infinite pieces. But since this is 0, the infinite pieces must cancel each other and the finite pieces must cancel each other. So the constraint, the wave equation, the stationarity condition on the metric makes the divergent pieces in both sides cancel each other. Now, even if we now ignore for the moment loop corrections, we just quantize the energy momentum tensor of the fermion, and we got this particular answer. And now, what about quantizing on the gravity side? The same thing. So we do that, and we find that we can't at this point. Now what happens is, and this is the point, when we expanded, we introduced h mu nu equals 0. The equation box h mu nu equals 0, we introduced h mu nu, box h mu nu equals 0 has a non-trivial solution and a trivial solution. But this equation is telling us that if this piece is non-zero, then the trivial solution cannot be allowed, because the sum of them has to add up to 0, and therefore it must be the case that h mu nu is of order h bar, because this side is of order h bar. And therefore, gravity is quantized by the coupling to its source. Okay. So if we generically quantize the gravitational field according to a standard equation with a wave function renormalization, then we would need to set z equals 2, because there are 2 helicity components, and that would be forced upon us by the matter sector. And if the matter sector consists of 4-component fermions and gauge bosons, then we would get that z is n minus m. So the normalization of the canonical commutators in the matter sector and fixes the normalization in the gravity sector, with the gravity sector adjusting to whatever its source may be. So whatever is over here in terms of all of the 0 points, they all have to add up to the 0 point of gravity. The gravity Z cannot be set equal to 1, which is what you do in canonical quantization. You have to fix it by its source. Okay, now, we'll skip that. Take too long. Okay, now let's go back to our question of we wanted the path integral to exist. Can we do it for Einstein gravity? No. Can we find an analog equation where gravity classical equals classical, quantum equals quantum? We can do it for conformal gravity. Very quickly, the Vial tensor was discovered by Vial. It's a remarkable geometric object. You make a transformation of g mu nu is e to the 2 alpha of x g mu nu, and all the derivatives of alpha drop out of this function, and c goes to e to the 2 alpha times c. That's, of course, is just like what happens in Yang-Mills and in electromagnetism. So you try as an analog of f squared is c squared. C squared has 4 derivatives, so the coupling constant is constant, is dimensionless, and so this is a renormalizable theory. You expand it out, it depends on r mu nu squared minus a third r alpha squared, and the equation of motion becomes w mu nu is t mu nu m. W mu nu is a somewhat ghastly thing, which was, I believe, first worked out by DeWitt, but it turns out that it becomes very tractable, and that's work I've done separately. Okay, so now let's linearize this theory about flat. So we introduce a fluctuation, calculate the first order. We introduce K, which is the traceless piece of H, because this is a traceless theory being conformal. And we look in the transverse gauge for K. You can expand K out in terms of 2 functions, e to the ikx and n dot x e to the ikx. And then you can write this K out in this form with all of these creation and annihilation operators. And the commutation algebra is a little bit unusual. Between the A and the B, you get a delta function, but between A and itself, you get 0. And some of the commutators of 0 is telling us that the Hamiltonian is of a non-diagonalizable Jordan block form, and I'll come back to that in a moment, with an incomplete set of vectors. And that's telling us, simply because these are 0 rather than 1, that the theory has a Hamiltonian which is not diagonalizable, and therefore the theory is not Hermitian, before you even start. Okay, but once we've done that, we now calculate the second order term, and now we set the second order term, which we can calculate directly, equal to the second order piece of the matter sector. And then we get that the total energy momentum tensor of the universe has 0 expectation value, because that's the stationarity condition, and that sets z equals 1. And it's non-zero only because this term is non-zero. Now, it's interesting, if we had n 2-component spinors and m gauge bosons, then we would find that z would be n minus m over 2. And you can do some phenomenology. Z has to be positive, and that means that n has to be greater than m. The number of fermions has to be greater than the number of gauge bosons. For 3 cross 2 cross 1, m is 12 and n is 16 for every generation, so n is greater than m. For SO10, m is 45, but n is still only 16. So you need at least 3 generations in order to maintain this condition. If you want to put all the generations in a single multiplet, you must use SO2n, where 2n is greater or equal to 16. And the only solution for SO16 is m is 120, n is 128, so you need 8 generations. You can have asymptotic freedom only up to SO20. And so if you were doing this in a grand unified group, SO16, SO18, and SO20 are the only available options. And of course, SO16 is the one that we see also in string theory. Okay, now going back to this relation, and this is the important one, and this is the one that replaces the previous, the one that I was showing you for Einstein, divergent plus divergent is 0, finite plus finite is 0. Now, 0-point fluctuations of gravity and matter take care of each other. However, the divergent pieces cancel all on their own, and what we measure is only the finite piece that's left over, because this is the vacuum and this is the excitations out of the vacuum. This term has an anomaly, that term has an anomaly, but the sum of them doesn't, because that's a stationarity condition, not a Ward identity. There's a Ward identity for this one and a Ward identity for that one, but for the sum of them, it's a stationarity condition. And therefore, the two anomalies cancel each other. And the solution to the anomaly problem is it's not canceled within the matter sector alone, it's quantized by gravity itself. You can do this for the finite piece. Let me only tell you very quickly that you can solve the theory and get a luminosity redshift relation. You can prove a general theorem. The deceleration parameter is constrained to lie between -1 and 0, no matter what the values of the parameters in the energy momentum tensor are. And this is the fit. And the lowest fit is the standard omega m equals 0.3, omega lambda is 0.7. And the top line is with deceleration parameter of -3.7. That's the accelerating universe data. And you can see that without fine tuning, we fit the data, and lo and behold, the answer falls out. Yes, exactly in this constrained region, which the theory forces upon us. Okay, now.
If you have, let's say, 3-4 minutes to convert.
Okay, so now let's go to the ghost question. Okay, now let me tell you why there cannot be a ghost problem. Take the Dirac action, where gamma mu is just the usual spin connection, and it was constructed so that it would be locally Lorentz invariant. But it turns out that as long as the fermion's massless, it's also locally conformal invariant. So we get local conformal invariance for free. I've argued it, and Tufte has argued, that there should be an underlying local conformal symmetry in nature. So this is a conformal invariant theory. Now you do the path integral on the fermions, and you generate a new action. And that action is the conformal gravity action, the one we had a few moments ago. Find it. The one we had a few moments ago is the same action, which of course it would have to be, because we started out with a conformal invariant field theory, and we just did an integral over the fermions. Now, when we're through, we've now got a fourth order action that's induced. Now we have an obvious question. Is there a ghost? Well, if there's a ghost in 8.2, then there must have been a ghost in 8.1, because the path integral integrating out the fermions is the same as a one-loop Feynman diagram in an external gravitational field, and you can't change the signature of a Hilbert space in perturbation theory. So as long as the standard model is ghost-free, this theory must be ghost-free too. If it were not, if this theory had a ghost, then you've just established that the standard model would not remain unitary when coupled to gravity. Moreover, since radiative corrections give you fourth order terms, you have to learn to live with them whether you like them or not. So Carl Bender and I have figured out how to do that. You write 1 over k to the 4. It's conventionally written as a difference between two propagators, but I could also write it as a derivative of a single propagator. This one looks like it's got a ghost and it has 2 gravitons. This one has no ghost and only has 1 graviton. And it's the second one, which is the correct one for the conformal theory. Now, why did we think there was a problem? Because if you take the 2-point function and you want to generate this propagator, you put inside the completeness relation with a minus sign, so you generate this minus sign. However, Carl Bender and I looked at this theory, studied the quantum version, and we studied the ground state, and we found that it wasn't normalizable. But the completeness relation requires normalizability, therefore this is not valid. And therefore, the standard reasoning that makes you think that there's a ghost is simply not correct. Okay. It turns out that because the theory is not Hermitian, if the ground state's not normalizable, we have to, we can't integrate by parts, therefore the theory can't be Hermitian. It instead is what's called a PT theory. And in that case, you study the overlap of the state with its PT conjugate. And then the completeness relation has a plus sign in it. All the norms are positive, but because this is not a modulus squared, because this is not the same as the Hermitian conjugate of that vacuum, we can generate the minus sign when we evaluate this quantity. Now, the states are not normalizable. You have to continue them into the complex plane to make them normalizable. Then the theory is well defined, and the domain of the measure needed for the path integral also has to be continued into the complex plane. So the way that we make the path integral exist is we first of all take the conformal theory, we reinterpret it as a PT theory, and we continue the domain into the complex plane, and then everything is consistent. One more surprise, what happens when we actually go to pure k to the 4? Well, this decomposition isn't valid when you have m squared equals 0 because this is singular. And so the wisdom that you got from the partial fraction decomposition is not valid. Let's see what does happen. Consider two oscillators. Omega 1 is omega plus epsilon. Omega 2 is omega minus epsilon. In the limit epsilon goes to 0, e to the I omega 1t goes to e to the I omega t, and so does the other one. So we've only got one eigenstate that collapse onto the same one. But where does the other one go? Well, you take the difference but divide by epsilon, and then the difference divided by epsilon, that brings along a factor of t, that goes into t e to the I omega t, and it's become non-stationary. So what happens is we lose an eigenstate, and the second eigenstate becomes non-stationary. Now, what happens to the eigenstate that we keep? The two of them originally were orthogonal, but then they become the same. So they can't be both parallel to each other and orthogonal to each other unless they have 0 norm. And that's why all of these terms here are 0. In other words, the graviton emerges as a 0 norm state and not as a positive norm state. So we get rid of negative norms, but the surprise is we finish up with 0 norms. So here's my summary. You've got to treat the divergent pieces and the finite pieces separately, and you can do that if you have a consistent quantum theory of gravity. But if you have a conformal theory, I didn't mention this, but let me just state it. If all mass length scales come from symmetry breaking, because there's no scales in the fundamental theory, and all scales, symmetry breaking is intrinsically quantum mechanical, then all length scales are quantum mechanical, but without length scales, there's no curvature. Therefore, curvature is intrinsically quantum mechanical too, and gravity is quantized by its source. To conclude, we note that at the beginning of the 20th century, studies of black body radiation on microscopic scales led to a paradigm shift in physics. Thus, it could be that at the beginning of the 21st century, studies of things like black body radiation, again, this time on macroscopic scales, might be presaging a paradigm shift all over again. Thank you for your attention.
Thank you, Philip. I hope you heard this quite loud applaud in the room. So I already can see a question here. Yes. Actually, 5 questions. So should we start from the, what do you say? Online first, if that's okay. All right. So first of all, Alberto has a question. Go ahead, Alberto. Unmute yourself.
Hello, thank you. I have a question regarding the renormalizability of conformal gravity. It's more a comment than a question, actually. So you said that conformal gravity is renormalizable. I think this might be true for gravity in isolation, but we have a paper, Strumi and I, where we proved that if you also add matter to the system, then conformal invariance is broken by loop effects. This is not something you see at 1 loop order, not even at 2 loop order. but you start seeing at a very high loop order, like 4 loops or so. But it is present, and you can see that because once you start computing these higher loop effects, the R² term gets generated. So Weyl invariance is broken then.
Yes. Okay. I haven't seen your paper, but thank you very much for telling me about it. But the issue here is, if I can find it, is we have this constraint which comes from cancelling the 0 points. Now, this constraint changes when fermions get a mass. And this Z becomes mass dependent. And I've discussed that also in my papers. It changes when loop diagrams are included. Now, I haven't looked at your paper, but I think the question that you're asking is, what happens to this equation when you're in 3 or 4 loops, where you have loops, not just in the matter sector, but also loops in the gravity sector? And how does this condition maintain? And that's something I haven't done. And if somebody can do that, that's very important.
Well, I'm saying that we did compute the running of the R² term, so the coefficient of the R² term in the presence of matter, and we found that this running is not 0. So even if the coefficient is set to 0, as you want to have conformal gravity, then if you add matter, this coefficient gets generated. Okay, I don't know. It might be true that for gravity in isolation, this coefficient does not get generated. This I don't know. I haven't proved. But if you add matter, as you should, because eventually you need matter, of course.
I don't have any choice. I have to add matter.
Yeah, you don't have any choice.
Yes.
If you add matter, there is this effect, and the R² term gets generated.
Okay. Well,
in the paper, we also discussed the fact that in the high energy limit, you could have conformal gravity, but as soon as you go down in energy, this R² term gets generated. So at accessible energy, you have to take into account the R² term too.
What about the R mu nu squared term?
The R mu nu squared term also gets generated. So you also have to keep that one. But I'm saying that it's not sufficient to just include the C² term.
Yes. Okay. Can you please send me what you've covered? And that's very interesting. Yeah. Thank you.
Sure.
We can postpone the rest of this to the discussion session. So we can leave time for some more questions. So there is another raised hand by Torieri. Go ahead.
Hi, Philip. Thanks for a great talk. Things like renormalizability and absence of ghosts are, of course, they're mathematically sort of hairy and formal, but there is actually sort of very straightforward physical interpretations, which, before Wilson, there was Bohr and Sommerfeld talking about compensator charges and stuff like this. And the basic idea is that to recover canonical commutation relations with the detector sort of remaining classical, if you want, is the charge over mass ratio has to vanish. Binding energy over mass. And if you reverse this in natural units, it's the same thing as saying that the detector scale and the ultraviolet scale sort of don't talk to each other. That's sort of the physical interpretation of all this formalism. And one immediately sees a problem with the uncertainty principle. Charge over mass, this was sort of Matvei Bronstein's original serious quantum gravity paper in the 30s. That charge over mass is 1, and 1 cannot be vanishingly small. 1 is 1. Yes. And this is sort of the physical. In your case, you say that the coupling constant becomes dimensionless. So what would be a sort of experimental setup with charge over mass vanishing? You see what I mean?
Oh, okay.
A Gedanken experimental setup. Because the big issue with quantum gravity is that as soon as you find the setup where quantum gravitational effects are important, you get black holes. I mean, this is another way of putting the charge over mass ratio into perspective.
Okay, well, I'm not sure I can answer you completely, but
sure.
One of the things that Dimas Kazanis, one of my collaborators, and I have done is we've solved the Reisner-Nordstrom problem for conformal gravity. And then you find that the charge term, which always went like 1 over r, the Reisner-Nordstrom correction also goes like 1 over r, whereas in standard theory, it goes like 1 over r squared. So the whole way that charge and mass are related is not the same as in standard gravity.
Well, so, I mean, charge just mean whatever couples to the detector, and in gravity, the charge is the mass. I mean, in the non-relativistic limit, of course. That's the issue. The charge over mass ratio is 1 because charge is mass. I wasn't talking about charge in general. Electromagnetic charge, you can make experiments where charge over mass is arbitrarily low. And this is a physical manifestation of the fact that electromagnetism is renormalizable.
Well, then you have to tell me what's the gravitational analog.
Mass over mass. I mean, yeah, that's the issue.
Mass over mass for sure is well.
Yeah.
Okay.
Maybe we can keep also this for a discussion, because there's a question that seemed pretty urgent. Benjamin, go ahead.
Not question, but yeah, thank you for this really nice talk. I have 2 very quick questions. The first one was when you showed this free fermion field and integrated out the fermion, you said that you get essentially your conformal gravity action, right? But
yes.
So I'm a bit puzzled because this seems like a one loop argument. I would expect that there are also higher order terms from integrated fermions.
Okay,
so and then that you conclude that your conformal gravity theory has no ghosts because there are these higher order terms which could influence things, right?
Okay, there are 2 different questions. Let me see if I can find this. Sorry. Yes. All I'm saying is that when I do the path integral, already in one loop, I generate a 4th order action. Now, either this has a ghost or it doesn't have a ghost, but it can't have a ghost because I started with the standard model, and the standard model doesn't have a ghost. Now, if you want me to go to higher order loops, I can do so, but I don't leave the original Hilbert space. Now, if you are thinking that in doing so, I somehow did obtain a ghost, then that's your problem, because you're just saying that the standard model is not stable under quantum fluctuations in an external gravitational field. I mean, it's as severe a statement as that. This is where we start. That's what we use all day. You just put in the quantum numbers, and then you do this integral, and this is what you get. Now, I'll make a strong statement. You can't change the signature of a Hilbert space in perturbation theory. So it doesn't matter how many loops you do, you can't generate states of negative norm in a Hilbert space which starts out with states without any negative norm states. I mean, that's a general theorem.
So let me comment maybe, but do you agree that this fermion field you have on flat spacetime, and this do you agree that this fermion model you have on flat spacetime and unitarity is discussed there, only there on flat spacetime?
No, I have not touched flat spacetime. I've just done this path integral in an arbitrary background gravitational field.
But I'm asking the question, the statement about that the free fermion model is unitary. This is
I'm sorry. I'm said that I take a Hilbert space of not just the free fermion theory. You can take standard SU3 cross SU2 cross U1 to all orders. Doesn't matter. You're in a Hilbert space which is ghost free. I now do radiative corrections of the fermion fields in an external gravitational field. I cannot suddenly induce negative norm states. But if I did, it's a problem for the standard theory. It's not a problem for conformal gravity, it's a problem for the standard theory itself.
And just saying, understand that unitarity is for sure when we have the free fermion on flat spacetime.
No. Unitarity is for sure when you have the all order SU3 cross SU2 cross U1.
Yeah, you can have the standard model, but I'm just pointing that this is, at least I understand that this must be on flat spacetime to really say that this is unitary.
Okay, maybe I should have picked my words. Let me pick my words more carefully. In the standard model, the Hilbert space contains no states of negative norm. If you wanted to argue that when you can couple the standard model to an external gravitational field, and you then start generating states of negative norm, then the standard model is incorrect. It's got nothing to do with conformal gravity. And also, the statement that there are no states of negative norm remains true when you do radiative corrections, because you're in a given Hilbert space and you never leave that Hilbert space. Now, if you want to say that we were formulating the standard model in the wrong Hilbert space, that it should have been formulated in the state with negative norm, that's a different question. But I'm saying that the standard model, as we know it, is a theory with a Hilbert space with no states of negative norm. Now we ask the question, you couple that theory to gravity. Do you now finish up in a theory with states of negative norm or without states of negative norm? It's one way or the other. But if you do finish up with negative norm states, then the standard model is wrong.
All right.
I mean, you can't get around that.
I think we should get going to the next talk. Maybe we can postpone this very interesting discussion for later, if that's okay. So thanks a lot, Philip, again. And this is the right material for a very good discussion later. But now let's go forward with Fabio. If you can share your slides, please.
Can you hear me?
Yes, yes,
Okay.
yes, we can. I guess Alex should make you go. Okay, perfect. Very good. Fantastic. Okay, so
Is that okay?
yes, yes. So let's start with the next talk by Fabio Scardigli on analyzing certainty principle and asymptotic state. Sorry. Go ahead.
Thanks a lot to the organizer for the possibility to give a talk here to this very interesting conference. And I want to tell you something about generalized uncertainty principle and asymptotically safe gravity. And well, this is a collaboration with Gaetano Lambiase in Salerno. Well, let me start with a brief reminding on the asymptotically safe gravity. In many quantum gravity approaches, the basic parameters that enter the action, such as Newton constant, electromagnetic coupling, the cosmological constant, and others, become scale-dependent quantities. Scale dependence is perhaps at the level of the effective action is perhaps a generic feature of ordinary quantum field theory. In gravity, in particular, the scale dependence is expected to modify horizon, thermodynamics, and quasi-normal modes of classical black holes metrics. In particular, improved asymptotically safe gravity black hole metrics has been obtained quite long ago by some seminal paper of Martin Reuter and Alfio Bonanno, and then studied during the years by many authors, for example, Sauer-Essig or Alessia Protania and many others. Essentially, we can summarize this procedure in 3 steps. We have a scale-dependent effective gravitational action, where the G, K, and lambda K are the running Newton constants and the cosmological constant, depending on K, which is essentially the energy scale. And the cosmological constant may be here approximated to 0, because in this case we just want to deal with a local black hole matrix. It is possible to define a dimensionless Newton constant in this with this expression here, and it turns out that this small g of k is governed by an evolution equation of this kind, which can be integrated, and then we can go back to the dimension for Newton coupling, which has this expression here. Immediately, we see here some deviation at the high energy scales, where gravity for very high energies should be supposed to the coupling supposed to go to 0, while on the contrary, for at low energy, we recover the classical space-time. Still, we have to establish a link between the energy scale k and the radial coordinate of our system, so-called the identification of infrared cutoff, and usually at least a kind of identification can be expressed by a function of this kind, where gamma is a parameter. At this moment, quite arbitrary parameter can be given some estimation of gamma. Essentially, is positive, but for example, you have different values for this gamma, at least in the generator. The energy scale Kr is essentially a modified proper distance. If gamma is 0, for example, it just Kr is 1 over r. And it is supposed to interpolate smoothly between the proper distance close to the r equals 0 and at infinity. With this identification of k, this relation between k and r, then we finally can write down the running Newton coupling constant, which turns out to have this expression here. Clearly, there is a correction with respect to the standard one, a quantum correction. Here you have h bar. At this stage, at least, omega tilde and gamma are essentially numerical constants. In the AS gravity approach, to obtain a renormalization improved, or also classical Newtonian general relativistic solution, the idea is to replace everywhere the Newton constant G0, the usual Newton constant, with the running coupling constant G of r. So, for example, for a spherically symmetric Lorentzian metric, the lapse function of the ASG Schwarzschild metric would read like this, where essentially it's just the Schwarzschild metric with G of r containing the expression that I just showed you before. This matrix is just per se quite interesting. For example, at large R, we recover, which means a low energy, we recover the standard Schwarzschild solution. While on the contrary, for small r, if you wish close by to singularity, actually, so at very high energies, we have the nice property that the actual singularity present in the Schwarzschild metric disappear, If gamma is different from 0, we can have a de Sitter or anti-de Sitter solution according to the fact that the product omega tilde gamma is positive or negative. In the case of gamma equals 0, still we have a disappearance of the central singularity, but in a way a little bit less smooth than the previous one. We have here so-called the conic singularity. Let me tell you now something about another framework, another possible description of the interplay between quantum effects and gravity, a so-called the generalized uncertainty principle. Generalization of the Heisenberg uncertainty relations have many decades of history. Right now, the first paper perhaps was the one of Bronstein before the war, and then during the years there have been many important contributions to this field. Perhaps one of the most important 30 years ago papers of Veneziano and Gross in string theory suggested that in Gedanken experiments on high energy string scatterings involving gravity, the effective uncertainty relation should read in this way, something like this. So you have here the standard Heisenberg term plus a deforming term proportional to the momentum transferred into the scattering. And this deforming term is suppressed by the square root of the Planck length, so it's actually very, very small. And there is a deforming parameter beta, which is not dictated univocally by the theory, although is believed to be of order 1, essentially. String theory, as I said, there are many different approaches. They bring all to the same kind of deformation of the standard Heisenberg. For example, you can consider Gedanken experiment involving formation of micro black holes, or you can analyze, as Michele Maggiore did, the Hawking radiation coming from large black holes. All these different approach points towards a deformation of this kind. Of course, once you have a deformed uncertainty principle, then you can encode that into a deformed commutator. And this has been done by many researchers, here I have just few names, but during the last 20, 25 years. So you have a deformed commutator and you can develop a deformed quantum mechanics. You can compute essentially many, many things with this deforming parameter. One of the many things that you can compute is a deformation of the Hawking temperature of a black hole. Actually, this can be done, if you like, in a more heuristic way, just repeating essentially the Heisenberg microscope argument, remembering that essentially the size of a detail of an object explored through a beam of photons depends on the energy of the photons that you are employing, and this is the relation, the Heisenberg relation. And of course, there is a GUP version of this Heisenberg relation, which reads like in this way. Well, now, if you consider photons close by, photons of the Hawking radiation close by to the event horizon, then you can imagine that these photons have a sort of uncertainty in the position of the same size of the black hole, geometrical size of the black hole. And obviously, the average energy of these photons of the Hawking radiation is linked to the temperature of the black hole, the Hawking temperature of the black hole itself. So, with this identification, immediately you translate this kind of relation into a relation between the mass of the hole and the temperature of the hole. You can observe here that if you push beta to 0, you just go back to the standard Hawking formula. And here, on the contrary, you have some deformation of the standard temperature due to the presence of the generalized safety principle. You can easily invert this relation, but it is more interesting to expand the temperature in beta, to be more precise, in 1/n² terms. And you have here the first term of expansion. Of course, you recover at 0 order the Hawking temperature, and then you have some corrections. Now, of course, the Hawking temperature can be computed. The canonical way to compute Hawking temperature is to consider the lapse, to find the zeros of the lapse function, and then from general principles of quantum field theory, you have to write down the temperature as the derivative of the lapse function computed on the horizon. So, for example, if you have a black hole, if you have a Schwarzschild metric, then the lapse is this object here, and you get the standard usual relation of Hawking. Would be possible to mimic the temperature predicted by the GUP in order to extract some information on beta, and in particular, the idea is to extract some relation between the GUP parameter, the beta parameter, and the parameters omega tilde and gamma of ASG, of the asymptotic safe gravity, by comparing the GUP deformed Hawking temperature with the ASG deformed Hawking temperature of the same black hole. In the case of ASG metric, the computation of the temperature can be performed exactly if you want, since you can use the lapse that we have seen before. And this actually has been done, for example, by Conan and Reuter in this paper of about 20 years ago. More interesting, perhaps, for our scope, is to just to do this by writing the lapse function of the ASG metric in the form of a small perturbation over the Schwarzschild metric. You can write down that lapse function exactly in this way, where here you have essentially the Schwarzschild metric and a deforming function, which is this object here. Then immediately you can write down an horizon equation. And you can solve the horizon equation to the first order in epsilon. And then you can expand the Hawking temperature in this deforming function epsilon. Actually, we are interested essentially into the first order of the expansion. By the way, it's very interesting the fact that this expression becomes 0 if computed over a function of the kind 1/r². And this will be interesting for a later consideration. So now, what is the idea? Well, the idea is just to compare the two expressions of the temperature. We have the expression of the temperature computed using the ASG deformed metric, with epsilon identified by this deforming function here. And on the other side, we have the temperature computed, Hawking temperature computed via the GUP. The expansion is of the same order, at the order 1/m², if m is the mass of the black hole. And then, of course, at least at the first order, you can make this identification, which gives to you a clear relation between the beta parameter of the GUP and the omega tilde and gamma parameters of the asymptotically safe gravity metric. Okay, this is quite quite general result, at least at the first order of this kind of expansions. It's looks quite trustable result. Of course, we can also try to go further and to give a numerical estimation of these parameters. As for the omega tilde parameter, we can we have seen that the ASG improved Newtonian potential can be obtained from the standard Newton formula, essentially by simply replacing the experimentally observed Newton constant with a running coupling G of R. So here we have the ASG Newtonian potential, which can be expanded for large R in this way. And at this point, first we see that the first correction is of essentially quantum, since here we have the H bar. And the idea, in order to extract a numerical value for this omega, is to compare this expression with the quantum corrected Newtonian potential obtained by John Deneuve and collaborators in a string of papers during the years. Essentially, Deneuve see general relativity as a low energy effective field theory. At ordinary energies, gravity is behave well, so to say. So we don't push energy too far, and so the quantum correction at low energy and dominant effect at large distances can be isolated. And essentially Deneuve obtained this kind of correction to the standard Newton potential. This kind of quantum correction, practically computing the correction to the first order in H bar, and computing this coefficient exactly, which has this value. Well, just comparing with the previous formula, you extract the value for omega tilde. As for beta, we can also use a similar argument, not exactly the same for beta, because beta appears in the expression of the temperature, not in the expression of a potential, but we can write down a metric mimicking the quantum corrected Newtonian potential of Deneuve, and again is just a perturbations, a kind of deformation of the standard spatial metric. These are the expression. Is still just the usual Deneuve expression. Simply have replaced with LP the GH bar and so on, but essentially the same thing. Actually, there is a term here of classical origin, not containing H bar, but it's a term going like 1/² so it's completely cancelled by this expression, as I shown you before. So now we computed the formed temperature using for epsilon this expression. While of course we have the formed temperature coming from the GOP, and comparing again at least the first order, the two first orders in the two expansions, we get a direct expression for beta. And since we know everything, Deneuve has computed exactly these at least if we trust the calculation of Deneuve, but this coefficient it's exact, so we have an exact value for beta, numerical value for beta, which again, as we expected results to be of order 10, essentially order 1 over 10. By the way, using these two values, the one from omega tilde and the one for beta, we obviously from the general relation between beta, omega tilde, and gamma, we can extract the value of gamma, which results to be 0. On this point, perhaps there could be some uncertainty, so to say, because as I say, the gamma is, it is possible that gamma is 0, but some different calculation gives for gamma different values. For example, as I said in the paper of Bolan and Reuter, gamma is 9/2. But okay, at least at this level, we have this prediction for the value of gamma, which entails a conic singularity at the very center of our black hole metric. So, well, actually, I think I have been quite fast because practically I'm going to my conclusions. We established the connection between the beta parameter of the GUP and the omega tilde and gamma parameters appearing in the asymptotic safe gravity formulation. And this is a quite general result. Then going to a specific calculation of John Donald by comparing our result with the quantum correct Newtonian potential, as I say, proposed by Donald and the relevant Hawking temperatures, we obtained sharp values for these three parameters, omega tilde, gamma, and beta. And well, I see my time. I think I'm quite ahead of time, but
this is perfect because we were behind schedule, so now we are on schedule. Thank you very much.
Okay, so I recovered it.
A double applause for you. Thank you for the very nice talk. So you can hear me, right?
Yes, sure.
Okay. So first of all, there was a question in the chat, and they asked, is there an analogy between this beta parameter and the parameter usually used in non-commutative geometry, this usually called theta, let's say? Is there an analogy?
Well, I wouldn't say there is a direct analogy because the two approaches, at least from the physical point of view, are a little bit different. But you can compute some connection between this beta and the theta parameter of the non-commutative geometry approach. And actually, this has been done. Is something done. I think 3 years ago in a paper of Milasi and Lambiase and another Japanese researcher. I forgot his name anyway. So you can establish a numerical connection between these two different parameters. From the physical point of view, I think I don't see so many, because of course non-commutative geometry is based on a clear hypothesis on the non-commutative coordinates and so on and so forth. The GOP is something starting more from the scattering Gedanken experiments, in which you try to repeat the famous Heisenberg microscope argument, and just when you do that, instead of ignoring gravity, on the contrary, you take into account gravity. And if you do that, you immediately end up with a deformation of the standard Heisenberg relation.
Yeah, very good. So then there's a question by Philip.
Yes. Well, Fabio, thank you. It's not an issue I've thought about, so this is very interesting for me. What I wanted a question. from what I remember of the work by John Donoghue, that was done within conventional quantum theory with the conventional commutators. So I don't see how it would connect immediately to the discussion you're presenting of theories where the commutators are not the canonical ones.
Yes, I know, of course, the work of Donoghue is done in, so to say, standard quantum field theory applied to general relativity. The idea is just to exactly to try to compare the same physical quantity, which is the Hawking temperature of a black hole, computed with two different approaches. One is the, for example, the Donoghue approach of a deformation of, not a deformation, say, of an expression of quantum general relativity at the first order in H bar, so to say. And the other approach is GUP, which would entail deformed commutators. But since you want to compute the same physical quantity, I mean, the temperature is one. The temperature of a black hole is one, at least. So comparing these two things, you can, at the same order of expansion in 1 over m and so on, you can relate these expressions. In particular, you can extract a value of the beta parameter of the GUP, which on the contrary, I mean, you have some string theory models in which you can predict that the beta is order 1 and so on and so forth. But as far as I know, you don't have a specific explicit calculation for the beta parameter of the GUP. At least in this way, you can have an idea of the value of this object.
Yeah, okay.
All right. And then there is a question by Alessia. Should I point to the...
Yeah, super fair. Yeah, so I think that the contradiction comes from identifying the temporal component of the metric in the weak field limit with the Newtonian potential computed by Donoghue. So I have been confused by myself for a long time, and I also had nice discussions with people, with Roberto Casadio, with Benjamin, about whether one can actually make this identification. And if you think this is tricky in general, because the Newtonian potential computed by Donoghue comes from a 2-2 scattering amplitude. So it is the potential on an interacting, possibly massive scalar field, while the potential in the coming from the 0-0 component of the metric in the weak field limit is the potential or on a test particle, so something that is massless and is non-interacting. So in principle, they are two different things. Now, in the case of simple models, they coincide, but this might be a coincidence. And recently, I think there was a very key counterexample that was found by Chris in his and Chris Ripken and Renato Ferrero in their paper on de Sitter scattering amplitudes, where one can clearly see that the potential, the 2-2 scattering, is very different in that case from the case of the weak limit of the temporal components of the metric for a de Sitter space. So, for instance, in the de Sitter scattering amplitude, you clearly see the effect of the Hubble horizon, while in the case you just add the cosmological constant on Schwarzschild spacetime, you don't see that. So they are two different things and they cannot be identified, I think. And this probably leads to the contradiction that starting from a quantum field theory that is, I mean, compatible with standard computational relations, you you wouldn't expect to have a generalized uncertain principle, but making the identification, you see it. I think the point is that one cannot make the identification.
No, but maybe I was not clear. I'm not doing any identification. I'm just using two different theories to compute the same thing. And I hope that, I demand, let's say, I demand that I obtain the same quantity. The same quantity. Of course, I'm well aware that I'm not identifying GOP with deformed with I don't know, ASG gravity, or identifying the GOP with John Donov model of general relativity and so on. I'm just trying to compute at the same order of accuracy a given quantity, which in our case is the Hawking temperature, and I find we found, not just me, but me and collaborators, we found some connection between the parameters, in this case, the parameters of beta of the GOP and the ASG gravity, or also some numerical identification, numerical values for these parameters. But I'm well aware that the theories are totally different. I'm not saying there is an identification of theories or something like that.
I was not talking about the identification of theories, but at some point you wrote like F, that I guess is your Laplace function, as 1 plus 2b, where b is the Newtonian potential. I think that this relation cannot be used straightforwardly in general.
Oh, so well, you are telling me that the correction computed by Donov to Newtonian potential is not a Newtonian potential. I don't understand very well. I mean, or
well, probably we don't have a lot of time to discuss now. No? So the chair is looking at me with. But yeah, we can discuss that later. But that is exactly the point.
Okay.
We have plenty of time for the discussion. Session is going to be certainly very, active. All right, thank you very much again, Fabio. And let's move on to Georgios. I don't know how to pronounce it, but forgive me. Share your screen. Hello.
Hey, yeah. I don't know, can you hear me? Oh, yeah, good.
We can hear you very well.
Hey, so let me share my screen.
Yeah. Perhaps Fabio has to unshare first.
Okay. I did. Sorry.
I was no problem.
Okay. Hoping with the.
Good, you see it, right? I think it should be fine.
It's not exactly okay. Now it's full screen.
Yeah, it's full screen. Should be okay.
And we are right on schedule. I'm very happy about it. Okay, so
good.
That's what. So could you please tell me how to pronounce your name first?
So, Georgios.
Okay.
Georgios, it's okay. George, whatever. It's fine. I hear to everything.
Okay, but we welcome you, and you tell us about field definitions, perturbative unitarity, and Higgs inflation. So, thanks.
Exactly.
The floor is yours. Go ahead.
Thanks a lot. First of all, let me start by thanking the organizers for this very kind invitation to give a talk at the nice workshop. So as you already said, I'm going to be discussing about Higgs inflation, and more specifically about the self-consistency of Higgs inflation. This is a work we did with Mikhail Saposnikov and Sebastian Zell. Actually, the timing couldn't be better because we're submitting the paper today. so it should appear on Monday. And yeah, so let's start. Oops. This is the rough outline of my talk. First of all, I'm going to introduce Higgs inflation, some very, very basic stuff that are necessary for me to carry on with the talk. Then I'm going to spend the bulk of my talk discussing the self-consistency of the model from the effective field theory point of view, and hopefully clear some confusion that has been around for a couple of years, quite a number of years actually. And then I'm going to briefly comment on different formulations of gravity and whether changing, let's say, gravity really changes something. And then I'm going to conclude. So let me first start with the basics of Higgs inflation. And actually, I'm going to take a not so common way to discuss things. I mean, at least, yeah, it's not the standard approach. So one starts by coupling non-minimally the standard model Higgs in the unitary gauge to gravity by introducing this term that so a direct interaction between the gravitational scalar curvature and the Higgs field. Xi is the standard non-minimal coupling. Phenomenology requires it to be much larger than 1, actually of the order of 10 to the 3, 10 to the 4. Then there is the standard Higgs potential that at high energy is relevant for inflation, asymptotes to its quartic form. And let me tell you why it works without actually doing any computation. This model works because during inflation, Xi h squared, the non-minimal coupling, dominates over Planck mass. And once it dominates, it's approximately scale invariant theory. So Planck mass is an explicit breaking of scale invariant, but a small one for inflation. In other words, you have exact de Sitter, but not exactly exact de Sitter. You have a slight deviation, and this slight deviation is exponentially small. And that's why it works. And this can be seen by making a field definition. Okay, actually, this whole scalar tensor theories, it's always a game of making field definitions and so on. So one more convenient, more conventionally goes to Einstein frame to untangle a bit the dynamics between the scalar field and gravity, meaning that we change the metric, we redefine the metric to bring the gravitational sector to its canonical form, which results, of course, into a non-trivial modification to the Higgs sector. After all, don't forget, there is no free lunch. This seemingly innocent coupling between scalar curvature and the Higgs field, it's a radical modification to the dynamics, and I will come back to this point later. Okay, so omega here is the standard conformal factor. It's a function of the field itself. It is scaled appropriately with the Planck mass. And as you can see, the effect of having non-minimal coupling with an appropriate change of variables results into a non-canonical kinetic term for H, as well as a rescaled potential. Okay, this is very important modification, and approximately for inflation that I'm only going to be focusing on inflation in this talk. The theory simplifies considerably. Okay, and it simplifies considerably because out of the conformal factor, as we discussed, H term dominates over Planck mass. So you have a highly suggestive form because it dictates, once we inspect the action at the high energy limit, it dictates that we make the field canonical via an exponential map. Okay, so H, the initial field Higgs, the non-minimally coupled field, and the canonical normalized field high that I call here are related via an exponential map. And this is simply manifestation of the fact that actually high is a pseudo-Lambo-Goldstein mode of dilatations which are broken when moving from the original Jordan frame to the Einstein frame. And since the map is exponential, and since the potential depends on inverse powers of the field, means that you're going to get exponential plateau. Okay, and this is why it works. Note that for high going to infinity, you get exact de Sitter. This is not exactly Higgs inflation. This is simply cosmological constant. So yeah, this is not strictly high to infinity limit Higgs inflation, but it's large. Very good. Let me also make a side note that this is exactly what happens in Starobinsky inflation, and that's why it's also very successful, because it deviates from de Sitter slightly, exponentially. It's exponentially close to de Sitter. Okay, and the way to see it is start with action and realize that the standard gravitational, which is the term which is linear in curvature, is a small explicit breaking of scale symmetry for inflation. And this, of course, becomes more clear in terms of the scalaron. Hi, you all are familiar with that as well, which is practically the same form as I presented before, up to a rescaled coefficient. Okay, again, the scalaron is the pseudonumber-Goldstein boson associated with a symmetry breaking of dilatations. So, flat potential corresponds to excellent agreement with observation. First of all, as I already said, CMB normalization requires that the non-minimal coupling psi be very large, order 10 to the 4th. And once this is fixed, then the theory, due to its the flatness of the potential, gives a very nice prediction for tensor to scalar ratio and R in excellent agreement with observations. And yeah, that's all as far as the quick and dirty introduction to Higgs inflation goes. And now I'm gonna be talking about self-consistency of the theory. Now, we have standard model and we have gravity, and we combine them. The moment we do that, we end up with a non-renormalizable theory. Okay, this is clear. Now, irrespective of whether we have a coupling of a non-minimal coupling to gravity. On one hand, if you have a minimal coupling to gravity, then the cutoff scale of the theory, it's the Planck mass itself. But in the presence of a large non-minimal coupling, this strong coupling scale shifts down, and it may shift quite significantly below Planck mass. And the decisive factor for the self-consistency of the theory is actually if it's valid, if it's weakly coupled and able to describe the phenomena that we engineer it to describe. And this is a very important question. It's, the zeroth order approximation to the self-consistency of the theory, to be able to be applicable at the energy scales we're interested in. Now, the information about whether or not the theory is applicable is built in. It's built in the theory itself. So the strategy to extract this information that I'm going to be following in this talk is actually to perform dimensional analysis. That's not the only way to do it. One can compute amplitudes explicitly by following exactly the same logic that I will follow, but for our purposes, at least for identifying at least a lower bound of the cutoff, this is more than enough. And this is actually the approach we took in the paper that we wrote. So what is the strategy? The strategy is to fix the background. I'm gonna be calling it H bar, and this background will correspond to inflationary dynamics. Although it can be whatever epoch one is interested in, the logic stays the same. Now, once you fix the background, we're gonna study perturbations on top of that. Now, the non-renormalizability of the theory translates into the presence of higher dimensional operator for these perturbations. And by reading the scale suppressing the leading of these operators, we're going to find the lower bound of the cutoff. This is a well-known strategy. So, first of all, let me start as historically, because that was the approach back in the end of 2010 that this question was studied to start with. First, let me take the small field limit. Okay, whenever it doesn't matter in which sector I'm gonna focus, be it scalar sector, gauge sector, fermionic sector. Don't forget we're talking about standard model fields, right? Then the leading higher dimensional operators are of this form. So they come suppressed by a scale m Planck over xi, which is much below the Planck scale itself. Now, this is a problem, and I put a question mark because, okay, I'm going to show that it's not really a problem because this is not the cutoff, but let me not get ahead of myself. So it would be a problem if the cutoff during inflation is actually in Planck over xi, because it would be of the same order of magnitude, modulo an order 1 coefficient, with the Hubble scale during inflation of energy. Okay, and would mean that my description is not completely trustworthy. Now, taking the opposite limit, however, that actually corresponds to inflation and not to the present day, that, because what I talked about before was the present day, but in the opposite limit, that psi h dominates over the Planck scale, Then in the scalar sector, I find that actually the operators are suppressed by Planck scale. And of course, this is not a problem because Planck scale, okay, it's much higher than Planck over Xi, which is the relevant energy scale I'm comparing with. And of course, I'm a bit too naive at this stage, okay? Because as I already told you, we would expect the presence of a new energy scale. And we cannot get out of it so easily, okay? The point is that I'm looking at the wrong place. So I'm looking at the wrong place because I'm employing unitary gates. And since I'm employing unitary gates, the scalar sector is kind of trivial in the sense that, okay, of course, not trivial in quotation marks. It's not trivial, it's non-trivial enough to give us very interesting cosmological phenomenology, but there are no surprises there. You can always find fielded definitions, you canonicalize, remove non-linearities to the potential, and so on. Now, this may give the wrong impression that the issues about unitarity and the issue about this new energy scale that is hidden disappears, okay? This is not the case, and actually, the only problem one faces is to pinpoint the location of the problem. Now, what is the essence of the situation? Let me forget for the moment about Higgs inflation and focus on standard model. And more specifically, I'm going to focus to the longitudinal gauge bosons of the standard model and take the scattering processes involving these guys. Okay. Now we have from the non-abelian field strength. These guys give rise to cubic vertices and quartic vertices involving only the gauge boson, and these at the high energy limit go as energy squared. Okay, here it's the gauge coupling G. It's not essential. I just wanted to make it clear what is the form. There is nothing. There's no difficulty in deriving the full expression, but I only care about the high energy limit. Okay, so G is the gauge coupling, E is the energy, mass MV is the mass of the gauge bosons, which on top of the electroweak vacuum, like we normally discuss these processes, is given by the Higgs expectation number. Now, on the other hand, we know that from the covariant derivative, Higgs, the physical Higgs, the excitations of the physical Higgs in the unitary gauge, mix coupled to the massive gauge bosons. Okay? And this coupling is essential, it's the whole essence of Higgs mechanism. Okay, because they're responsible for cancelling this E-squared behavior and making the amplitude at high energy not diverging. Now, this is a very delicate cancellation that happens in the standard model, and it's possible if and only if the cubic vertices are proportional to the mass of the gauge bosons themselves. So the cubic mixing between H and between the Higgs and the massive gauge bosons are proportional to the mass of the gauge boson. Now, back to Higgs inflation. Now, by coupling the field to gravity, I'm changing its dynamics in a non-trivial manner. First of all, I'm making the gauge bosons to acquire an effective inflationary mass, but this time it's proportional to m Planck over square root of Xi. They're super heavy. Okay. Now the problem is that the Higgs interaction with the vectors are actually exponentially suppressed as well. They're not proportional to the masses of the guys anymore, but they're practically decoupled as far as inflation is concerned. Now that would be fine, but at the same time, the kinetic, the field strength tensors, both the non-abelian and the abelian one that hide inside the kinetic term and the self-interaction terms of the gauge boson, are completely unaffected by going from Einstein to the Jordan frame and vice versa. Actually, from Jordan frame to Einstein and vice versa. And it's exactly this partial modification of the gauge dynamics that lies in the heart of the problem. So this is a cartoon of what I said in the previous slide. You have the trace of F² term that gives rise to the self-interaction of the gauge bosons, which are unaffected, apart from the fact that their mass coming from the covariant derivative of the Higgs, which is proportional to m Planck over square root of Xi. Okay, and on the other hand, you have the interaction between the Higgs and the massive gauge bosons, which is exponentially suppressed, making also the amplitude exponentially suppressed, so there is no cancellation. Thus, if there is no cancellation, then perturbative unitarity for the theory is lost exactly at the mass, at the scale suppressing this E-squared term in the amplitude, the corresponding amplitude. And this is exactly the mass of the gauge bosons, which in turn is proportional to m Planck over square root of psi. This is well-known situation, okay? And understood very well. And also, let me give you the full picture, the big picture, as I say here. The cutoff is background dependent, depends on the Higgs. So during inflation, as I discussed, is m Planck over square root of psi. Then it decays with quadratic power of the field during reheating and relaxes to its present day value, which is m Planck over psi. So to reiterate, m Planck over psi is there, but it doesn't correspond to the cutoff scale during inflation. That would be a problem. It's the cutoff scale of the theory today, and it's not a problem because it lies well above any experiments that we have. Energies reached by experiments at this stage. But during inflation, where we reach energies comparable to m Planck over psi, it would be disaster if the cutoff was actually of this order. Hopefully, that's not the case. Now, it's quite logical to wonder what happens if we didn't work in the unitary gates. As I said, it's a matter of convenience. Traditionally, Higgs inflation is studied in the unitary gates for convenience because the scalar sector only involves the physical Higgs, which is actually responsible for inflation, irrespective of whether works in the unitary gates or not. This is what carries the dynamics. But what changes if I deviate from that is that I would have explicit presence of the would-be Nambu-Goldstone modes in the scalar sector, making it non-trivial. And of course, don't forget that, again, we're talking about standard model. These are not some exotic degrees of freedom. These are actually the longitudinal components of the Gates vectors. Okay? It's simply a matter of, where to look. Okay? If you keep them into action, they're going to make the scalar sector non-trivial. If you remove them from the action, not remove them, if you fix the gates, you give the vectors a longitudinal component, which is the would-be Nambu-Goldstone mode. Nevertheless, although nothing should change, it can happen, and actually it happens that a not so clever choice of variables may result into false appearances. And actually, I'm going to make this point clear by making by discussing the simplest possible toy model that we could come up with. But I promise it's exactly the same situation as what happens in Higgs inflation. So take two scalar fields for the sake of the argument. In Higgs inflation, we have 4 of them. And assume that the dynamics is captured by the action that I'm writing here. So you have the standard kinetic terms, and then you have some higher dimensional operator of this specific form. Of course, we engineered it to be of this specific form. Now here, lambda tilde is carries mass dimension, and C is a constant. Okay. So at first sight, what do I see? I see two fields that appear to interact non-trivially via some derivative of C, and since the scale lambda appears explicit in the action, it's very tempting to identify it with the cutoff. Okay, because as we discussed before, we're performing dimensional analysis here. So these are the leading operators. There may be other stuff we don't care about, but since these are the ones that are the leading ones, sorry, I should identify lambda tilde with the cutoff. But at second thought, one realizes easily that appearances are simply deceiving. This action describes two fields which are completely decoupled, and lambda tilde is a spurious thing. It's a spurious scale simply because I didn't use a smart choice of variables. And to see it even more explicitly, it's kind of trivial to complete the square and rewrite the action in the form that I've written it here. Then it's quite easy to see that we need to introduce two new fields, phi 1 and phi 2, given by these expressions. And once you do that, you have the true nature of the toy model that is revealed. Okay, and it's nothing more than two completely decoupled free scalar fields. Now, since we covered in detail this toy model, I'm going to show you what happens in Higgs inflation, which is pretty much the same situation. Now, the first choice of variables I'm going to be talking about is the Cartesian Parameterization, the standard one for the Higgs doublet. I'm going to come to it soon. Now, where do I need to look? As I said, we need to look at the proper place in order to identify the cutoff, depending on the choice of gauge or variables that we are using. In this particular case, we need to focus on the kinetic sector of the Higgs doublet. This is the non-trivial part now. The potential gives contributions which are exponentially small, as we already said. The potential itself is it's exponentially small correction to the jitter, to a cosmological constant. Okay. So what we need to focus on is the scalar sector of the theory. Due to the non-minimal coupling, the scalar sector of the theory has been modified quite non-trivially. And it has the scaling with 1 over omega square, plus this dimension 6 operator. Of course, this is, I presented you before with the unitary gauge analog of this expression, but okay, here for completeness, I'm writing it here. And yeah, let's try to understand what happens. We take the Higgs doublet in its Cartesian form. So pi's are the would-be Nambu-Goldstein modes, h bar as before is the background, h is the physical Higgs. We plug h into the relevant part of the action given by this expression, then expand in terms of h and pi, and keep terms which are more quartic in the perturbation. Don't forget we're looking at 2-to-2 scattering, so quartic in perturbation stuff is up to quartic in the fields is what we're after. Then we're going to need to normalize canonically the kinetic term by some trivial scalings that depend on the background, and then take the inflationary limit, which is actually psi h square, much bigger than M Planck square, that we've been taking it from the beginning. Once one effectuates these steps, ends up with the following after some massaging, and I have put in green the confusion. Okay, because we noticed that this M Planck over psi scale appears explicitly in the action, and this is confusing. Okay, it's confusing because we already established in another choice of variables that this is not the cutoff, has nothing to do with the cutoff. The cutoff is higher, and it's actually square root of, M Planck over square root of psi. On the other hand, we find some higher dimensional operators which dominate over the rest of the terms in the expansion, and are suppressed by M Planck over psi. So what's going on here? And what is going on, I'm answering immediately, is that just like in the toy model, we just are not using the proper set of variables to understand what's going on. Because it's trivial also in this case, like in the toy model, to complete the square, introduce a canonical field that removes this redundancy, and actually end up with something that only depends on M Planck over square root of psi, as it should. And of course, the significantly lower fictitious scale, it disappears. It's simply an artifact of not employing the appropriate variables. Now, of course, there is no confusion after all, but it's important to make sure that once you try to follow this logic by identifying the cutoff by performing dimensional analysis or by computing amplitudes, because especially for dimensional analysis, make sure to eliminate redundancies at the amplitudes. Even if you start with a redundant form, there is nothing wrong with working with that. S matrix is invariant under this sort of field definition. The point is that if the computations are done properly, at order M Planck over psi, everything must vanish. But the problem with actually explicitly computing amplitudes is that they're error prone. Okay, so one should simply need to be careful, I would say. And now I'm gonna show that there exists a better choice of variables, and this better choice of variables is not something cryptic or weird. It's simply the usual exponential parameterization for the Higgs doublet, which of course is not the only one which may serve the purpose. It's just the one that most people are familiar with. Actually, our collaborator Sebastian Zell came up with yet another parameterization for the Higgs doublet, not so standard one, that also serves the purpose of what I'm talking about here. Now, again, the starting point is the kinetic sector for the Higgs doublet, but now I'm going to work with the exponential parameterization for the Nambu-Goldstein modes. Here, the taus are the standard Pauli matrices, and I've rescaled appropriately for dimensionalism with h bar. That's what we do even if we're expanding around the electrode pattern. But of course, here I'm expanding around h bar, which is inflationary background. Now, the methodology is exactly the same as in Cartesian analysis. I take h, I plug it into the action, I expand in powers of h and pi, keep the terms which are relevant for my discussion, And after canonically normalizing the kinetic terms and taking the limit, which is inflation, I end up with something that actually leaves no room for confusion to start with. There is an action of two scalar fields, chi and sigma, actually four scalar fields, sorry, with the leading higher dimensional operator coming hand in hand with m Planck over square root of psi. Okay, without the need for any additional filter definitions and so on. Before actually moving to conclusions, I would like to spend a few slides discussing what happens if we change gravity, since this is quite nice and new trend to actually work in different formulations for general relativity, like for instance Palatini that I'm going to be discussing here. Because the logic, first of all, let me say that it's exactly the same. You start with a Higgs field coupled non-minimally to scalar curvature. The only difference being that in Palatini formulation, the connection and the metric are independent fields, meaning that after doing the Vial scaling to canonicalize gravity, one does not get the dimension 6 operator because the scalar curvature is inert, it doesn't transform inhomogeneously under Vial scaling. Okay. Now, the scalar sector is much simpler than in the metric case. Not let me say it once again. Simpler or simple does not mean trivial. By no means. This modification, this 1 over omega squared, is an important modification that actually makes possible to have good inflation even for this case. Okay, let me make it clear. No, but importantly, there is no inhomogeneous piece. It's this term only. It gets rescaled the kinetic term by power of conformal factor. No, can this affect the self-consistency at least as far as inflation is concerned? I think that this the answer to this question is known. I don't know how well known it is, but it's negative. Okay, and the logic is exactly the same as in the metric case. The gauge bosons still get effective inflationary masses. These masses are still proportional to m Planck over square root of psi. Still, the Higgs excitations are heavily suppressed, but not that much as in the metric formulation. Nevertheless, the mechanism which is responsible for this cancellation of the diverging part of the amplitude, it's null. So, as before, Palatini formulation comes with the same inflationary cutoff as a metric formulation. Now, actually, I'm in my conclusions. I think also I'm in time. And what are the take-home messages? The first is that the standard model may have been responsible for inflating our universe. The predictions of Higgs inflation, be it in the metric or the Palatini or the Einstein-Cartan or whatever formulation, are in excellent agreement with the latest data. Even though it has been non-trivially modified compared to the vanilla standard model, it remains a self-consistent weakly coupled effective theory. Now, depending on the choice of gates or the choice of variables one makes, it is important to be careful where to look at to identify the issues with the theory. Okay? And once you do that, be careful to choose the suitable variables in order to study the problem. And yeah, be careful not to fall into the trap of these artifacts and redundancies if not so suitable variables are chosen. Thank you very much for your attention.
Thanks a lot for the nice talk, and also very good on time. I didn't even have to say anything. All right, so
no, I'm okay with time, right? It was 35 minutes or so.
More than okay. So, are there any questions from Zoom? Yes, I see I raised hand. So please unmute yourself. Go ahead.
Hi. Yeah, thank you for a nice talk. Maybe I misunderstood, but I don't quite understand the motivation here. So you are talking about the standard model Higgs inflation, right?
Yes.
And I guess the reason you chose psi around 10 to the 4 is because you chose the lambda about 0.1.
Yeah, but otherwise it's not the Higgs, the standard model Higgs if lambda is not 0.1, right? That's the whole point, the whole essence.
But the lambda runs.
Sure.
But if you take into account the running of lambda, it becomes a negative, right?
Not really. Depends on the extra assumptions, right? I mean, if standard model is valid up to Planck scale, the lambda is fine. This has to do with the stability and metastability of the vacuum, right? That's what you're asking.
Right. So what you're saying is lambda is 3.1 during inflation scale.
So it can run, of course. It may become even smaller, but still, it's not going to become negative. If the vacuum is not metastable, then it's fine.
Okay, so no. So okay, so the reason I'm asking this is because if lambda is small, then psi doesn't have to be large.
I understand, but still, lambda can never be that small. So psi is redundant. It may, of course, psi can become, say, of the order 100 or a few orders of magnitude below, but still it's going to be large.
I see. Okay, thank you.
Yeah.
All right, I see no other raised hands on Zoom, so let's turn to the live audience. Does anybody have a question? We have a few minutes. No? Oh, actually, there is a question in the chat. Let's see. So I'm reading from the chat. How can the model of Higgs inflation overcome the shortcomings of standard cosmology, such as the graceful exit problem? Also, they thank you for the very nice talk.
Yeah, thank you. So, I mean, it's a slow roll inflation, right? So the graceful exit problem is by definition not there. I mean, I would have the graceful exit problem if I was talking about exact de Sitter. So that would be the case. But now there's no such thing. I mean, I have inflation due to a scalar field. Eventually, it will end. It's standard chaotic inflation, nothing out of the ordinary. With a specific, of course, plateau potential that makes it very nice as far as observations go and predictions go. But it ends, inflation ends.
All right. So, and then there's another question in the chat from someone else. So as far as I know, the scalar field is only scale invariant if psi is 1/6. How can the theory be conformally invariant with large psi, as you said in the beginning?
Yeah, I think it's a matter of, there's also some confusion here. So the theory is scale invariant respectively of the value of the coupling psi being 1/6. Now, if the Planck mass is not there, is 0, and the coupling is equal to 1/6, then the theory is Vial invariant. Conformal invariance, I'm not sure it's what I would call it in curved space. It could be Vial invariant in the absence of the Planck mass, and for coupling equal to 1/psi. Now, if I forget M Planck, the theory for arbitrary values of psi is invariant under dilatations. Okay, so take H, rescale it by constant, and take the metric, rescale it by a constant with appropriate power, and you're going to end up to the same theory. Okay, that's what I mean scale invariant, not conformal invariant. Conformal invariant has to do with flat space. Vial invariant would require both the absence of M Planck square and the conformal coupling 1/6.
But so sorry, it was me who asked the question. So I for some reason I missed some of your answer. I don't know if it was my computer. But so what is conformal invariant for you exactly? Is it a transformation of the metric and the scalar field with some conformal factor and then?
No, conformal invariance is a well-defined notion for flat space. Now, in curved space, the generalization of conformal symmetry, and probably that's what you're asking, is Vial invariance, right? So you rescale with appropriate factor H and the metric, and you ask your question whether or not you end up with something which is the same. And for this to be the case, because the Ricci scalar is a function of the metric, and if the conformal factor depends on the coordinates, you get an inhomogeneous piece. And the coefficient of this inhomogeneous piece is psi h squared, and you need it to be -1/6 to cancel the homogeneous piece coming from the kinetic term of the field. That's what you're talking about?
I mean, so you're telling me that you only transform the metric, but not the scalar field.
No, I'm not saying that. I'm saying that.
So what is
it's
exactly the
different thing to have-
transformation? Don't give me the name because I'm like kind of confused about the different names that the different transformation have. Like, what is exactly the transformation that you are doing to your fields that makes it invariant, you know, for this theory?
So take H, send it to lambda times H, whatever, alpha times H.
Okay.
Take the metric, send it to alpha minus 2 times the metric, and you end up with the same thing with alpha a constant. This is a scale invariance. Okay, and it has nothing to do with psi being equal to 1/6.
With alpha a constant over space-time, basically.
Yes. Now,
Okay.
take alpha to depend on space-time.
Now,
And
okay. Okay. So if alpha depends on space-time, then what?
No, but if alpha depends on space-time, we're not talking about scale transformations, we're talking about Vial transformations, right?
Okay. Yes.
So take M Planck, put it to 0,
Mhm.
take alpha to depend on space-time, you're going to find that a rich scalar spits out an homogeneous piece containing two derivatives of alpha.
Mhm.
And the kinetic term for H also spits out a term containing, actually the rich scalar has, let's say, one term linear in alpha, in derivative of alpha, and a term quadratic in alpha, in derivatives of alpha, same with the kinetic term. And to cancel these two and to have Vial invariance, you need to fix psi to be 1/6.
Exactly. Yes.
Good. I'm not talking about that. This is not scale invariance. This is Vial invariance.
Okay. Thank you. So basically, scale invariance is just a field redefinition by a constant.
It's by definition.
I mean, you can
it's a
think of
dilatation. It's a dilatation, a global
but
dilatation.
it's a constant dilatation. Okay.
Yeah.
Okay. Thank you.
Can I just very quickly comment?
Yes.
If NP squared is 0, no matter what xi is, every term in the action has dimension 1/4. So if you scale with a constant, the action remains invariant. But if you scale with a function, then it only remains invariant if psi is a 6.
Exactly.
So you're going from global scale invariance to local scale invariance. But for any value of psi, you always have global scale invariance.
Yeah, and also let me add something, because in the case of in this Vial symmetric theory, in this particular one, H is redundant, right? It's killed by the transformation itself.
Mm-hmm.
So it has no dynamics. It's GR with cosmological constant. In the absence, of course, of M Planck.
Okay. Thank you very much. Now I
Sure.
understand.
All right, so we have another question by Alberto. So go ahead. We have
Hello.
some time. Yeah.
Thank you. I have a question regarding the Palatini part.
Yeah, sure.
And so, is Palatini Higgs inflation equivalent to metric Higgs inflation or not?
Now, in what sense? You mean prediction-wise?
Yeah, physically, prediction-wise.
It still gives inflation. No, they're not exactly the same. They have similar predictions. So NS is the same, but R is predicts a smaller amount of gravitational waves, Palatini.
I see.
So you see, I mean, it gives plateau, but it's not really exponential. It's a hyperbolic function now that we're talking about for Palatini. So there are some differences as far as R is concerned.
Okay.
And there are also differences as far as reheating is concerned, to my understanding, especially when it comes to this cutoff.
Okay, but the two theories eventually can be, I mean, the Palatini theory eventually, if you just have the standard Einstein-Hilbert term, can be written as the standard Hilbert term plus some higher order terms, right? Because you can integrate out the connection. So what is what is causing these different predictions are higher order terms.
No, exactly. But in the Palatini, it's exactly what we say. So you get Palatini, you integrate out the connection, but now the connection on top of the metric also gets a piece proportional to, say, the non-minimally coupled scalar, because it's more general than Higgs. And this, the form of this extra piece that you get once you plug it back into action after you integrate out the connection is exactly equal to this dimension 6 operator that originally stemmed from the inhomogeneous piece of the Ricci scale, let's say, and it kills it. And that's why you don't have it anymore. You simply get the rescaling by the square root of G in the kinetic term of the Higgs.
So when you integrate out the connection, you get Einstein-Hilbert term plus the Xi term plus this high order term. Is dimension six.
And then exactly, and then you get you go to Einstein frame and you cancel exactly this dimension 6 operator.
But then, so if you have a dimension 6 operator, don't you have to add in your effective field theory all dimension 6 operators?
No, but that's the point. I mean,
at the level of effective field theory, if you go up to 6
no, but you see, these are operators that are generated from the theory itself. So one, in one way or another, needs to decide what would be the starting point. I mean, and the starting point is, okay, you write the theory in the Jordan frame, coupling it non-minimally to gravity and study the dynamics there by truncating to the lowest possible, to the lowest operators. In the original formulation of the theory, there is no dimension 6 operator there, right? This comes only after you integrate out the connection. Okay, now you can open Pandora's box and supplement, with all possible operators, but I don't think that would be the logic one is taking here. So this is dynamically generated operator in the sense that it follows by integrating out the connection, as you already said.
So you think that?
No, but why in Higgs inflation, for instance, don't we also write all the possible dimension 6 operators that appear after conformally rescaling, after going to the Einstein frame? It's the same logic here. We keep only one operator right here, this one, that comes from the homogeneous transformation of R. Same logic as is in Palatini.
Okay, I see. Okay.
All right, very good. I think we have time for maybe one more short question, but I see nobody asking for it. So I think we can thank, Georgios. Is it decently pronounced? Well, anyway, thank you.
It's fine. Yeah. Thanks a lot. Thanks. Thanks for listening.
My apologies for my butchered pronunciation, but anyway, really nice talk. I really enjoyed it. And yeah, so we can move on to the last speaker of the day, Alexander. Yeah, hello. Yeah, we can see you. Could you? You're muted.
Yes, just a sec.
Hi.
So that I would see which screen am I sharing.
Hi, Sasha. Fortunately,
hey, good to see you. Sorry, imagine I managed to get locked out of my office, so therefore it took a bit longer. But it's okay. So, can you see it now?
Yes. Yeah.
Okay.
Perfectly fine. So I think we can, we can start right away, I would say. So welcome, Alexander, and so you tell us about ghosts without runaway, right? So welcome, and yeah, whenever you're ready, we're perfectly.
Yeah, I think I'm ready. So thanks a lot, guys, for organizing this event. I wish I could join you in person there in Portugal. I bet you it's a lovely place, even though I have never been to the country. And thanks to Losha for inviting me. So basically today I will tell you about our recent work and about ghosts. And actually these ghosts are pretty nice and cute. So this will be based on this paper, which we published in PRL with Cédric Defayet and with Shinji Mukayama. And basically, if you want, the main message of this talk is actually super simple. Namely, some systems with ghosts can be manifestly stable. Okay? So that's if you want, that's what you want to pick up home. And then let me just remind you what are ghosts. Basically, for me, ghosts are systems with negative mass, and I will tell you in which sense negative mass, or actually kinetic energy which is unbounded from below. Let me go to more details. So let me point out the following mechanical analogy. So usually when we deal with ghosts, we think about some gravity modifications, cosmology, something else. So let's look at, say, curvature perturbations in cosmology. So usually the action looks like this, where there are two free functions, namely the Z and C. And I don't know whether you can see my my pointer. I don't think you can see it actually, but whatever. You can imagine that you see it because somehow I don't see it, but whatever. So basically this capital Z and this capital CS, not capital, but C with capital S, these are two time-dependent functions which usually sort of say define the properties of the action, which depend on the theory you consider, okay? So if you look now at the Hamiltonian for each mode, because this is a linear system, so you can really look at sub-Hamiltonians, then it takes this form where P is the canonical momentum, and index K means that this is for particular Fourier mode K. And if you compare it with normal standard Hamiltonian for normal harmonic oscillator, you will see that actually this mass does correspond to this function Z, and the omega corresponds to CS squared K squared. So of course, basically what we are doing is in cosmology is generically some bunch of harmonic oscillators, if you want, a continuum of those with time-dependent masses and time-dependent frequencies. Okay. So now, if you want to go, what are the possible instabilities for such systems? Usually people think about ghosts and gradient instabilities. Namely, we look again in this action, again in this H. And then first type of instability, which is called gradient instability, it's when this sound speed is imaginary or sound speed squared is negative. And that generically implies that your curvature, say, perturbations, or whatever cosmological perturbations, they behave, they grow exponentially. And basically, the point is that this rate of instability depends on linearly on K. So the larger is your K, the stronger is your instability. So this is, if you want, mathematically speaking, what is well known as an elliptic system. And there is no normal time evolution for elliptic systems, okay? Another option is ghosts, where their function Z is actually negative. Okay, of course, important thing is that it's negative with respect to something else. Clearly, if had we just considered this action isolated, we would not care, because when we switch the sign of the action, it's completely irrelevant if this action is the total action. However, of course, there's normal fields, normal standard model fields, and their sign is fixed. And in my signature convention, it's plus. So therefore here, if you have minus, then it's a different sign from the sign for standard model. And looking at this analogy which I discussed on the previous slide, this ghosts would correspond to actually a bunch of these oscillators with negative masses. Important thing, it's not negative mass squared, because this would be tachyon. This is really mass, not in the sense of mass of any particle, mass in the purely mechanical sense, mass for the corresponding oscillator for each of the modes. This is the, so to say, mechanical mass. Okay, and because this instability or potential instability is purely due to interactions, it's not related to any linear analysis. So the only way to see it is when interactions are switched on. And of course, because we're dealing here with gravity, at least there is unscreenable, unkillable, so to say, gravitational interaction. And what does it do? So for example, through the graviton, let's say this G is a graviton, you could write easily this three-level diagram And this diagram describes actually the interaction through gravity of photons and this, let's say, curvature perturbations. In most naive situation, in each of these vertices, there would be just 1 over m Planck. Therefore, the total amplitude of this process is 1 over m Planck squared. So therefore, the rate is the amplitude squared is 1 over m Planck to the 4. And now, if you want to really estimate what is the real rate per unit time, per unit volume, so you need to have dimensions 4, mass dimensions 4. So therefore, you need to write some dimension for parameter power 8 there. And usually people think that this is a cutoff. Of course, here the major subtlety is the following, that if this diagram, basically if the theory were Lorentz symmetric, then there would be boosts. And these boosts would introduce you actually infinite phase volume, because you would boost them and do it in all possible frames. And therefore, this rate would be just infinite. That would imply that your perturbative analysis is actually completely wrong. So if you have preferred rest frame, like it is the case in cosmology, and somehow you assume that your cutoff can be chosen in this rest frame, that it makes sense that somehow this cosmological rest frame is not transferable for this UV physics, then you will write this cutoff power 8. So you see that this instability rate is strongly cutoff dependent, strongly UV dependent, but not infinite, okay? By the way, you are free to interrupt me at whatever moment of time, so you are even welcome, because otherwise we will all forget what was it about. And take into account that I don't see chat, so if you need to intervene, so please say your comments. So basically, this, contrary to this instability due to the imaginary speed of sound, this instability is only due to interaction. So basically, we built scissors out of ghosty matter and normal matter. These scissors implies that they interact, right? Both sides. There is total energy, which is sum of these energies. And as time passes, the whole thing interacts, and the scissors just can open up. Why would they open up? Because, well, they conserve energy. Nobody precludes them of doing it. Total energy is conserved, but they can open up forever as wide as you want. So they're imaginary scissors, right? So, and this is usually the problem, that interaction would create you instability. And this instability is just connected to the statement that the total energy is not positive definite anymore, and it does not bind you to stay in a finite region of phase space. So basically, you can conserve energy and move to infinitely remote parts of your phase space. Okay, so that's general expectation. That's how most people would think it should work, and that's why we think that ghosts can be a problem, right? And of course, here the key point is in the needle, which actually holds these two scissors, basically these scissors together, right? And that's what we are going to abuse a bit later. So now, but let me remind you first, probably in this conference is kind of pointless, but let me remind you, why are we interested in this systems at all? Why are we interested in potential ghosts? And there are different reasons one can invoke or one can recall. For me, the reasons are the following. So formally speaking, they could provide interesting cosmology, like exotic things, like phantom dark energy, which you can also get without ghosts, but nevertheless, which you can only realize if your Hamiltonian is unbounded from below. You could organize bouncing universes. You could even have inflation with blue spectrum of gravity waves. So all these things actually can be done without ghosts in the spectrum, but with the Hamiltonian density unbounded from below. And formally speaking, the scissors argument would hold anyway, though perturbative this diagrammatic calculation would not. Another point is that, as we heard even at this conference, people are interested in systems with higher derivatives. And higher derivatives actually imply generically existence of ghosts due to the Ostrogradsky theorem. Of course, there are exceptions. And in some cases, exceptions are based on the point that you have built-in constraints. You could have gauge degeneracy, or you actually introduce high derivatives for those degrees of freedom which used to be constraints. Like in f of r gravities, it is the case that, of course, the scale factor is not a dynamical degree of freedom. You promote it to become dynamical, but you basically start from this degree of freedom with wrong kinetic, basically sign of kinetic term. And therefore, when you promoted it to become a real degree of freedom, this sign is actually okay. Turns out to be okay. So that's kind of miracle of this f of r. And this is closely related to the point that renormalizability of gravity requires to write your square of curvature terms. And we don't really properly know, at least not me. Unfortunately, I missed Philip's talk because we have visitors here. And at least I don't know how to deal with these high derivatives in gravity. But formally speaking, if you do everything in Lorentzian signature, high derivatives, this high curvature terms, the square of curvature implies existence of ghosts there. And then they're more interested, like more fundamental or deep questions, which are not attempt to solve anything, but nevertheless, to me, I think that's very interesting. So questions related to entropy and thermodynamics, because you see, if you have energy which is unbounded from below, it's not entirely clear how to do normal thermodynamics. And finally, another kind of more ideological question is that we know that naively charges in gravity are all positive definite, because localized sources in gravity, normal Einstein gravity, always have positive, basically mass or positive energy. And in that sense, charges in normal gravity are always positive. So there is no way to introduce negative charges and screen gravity. And of course, if we were able to screen gravity, this would imply that UV behavior would be softer and nicer. So this are kind of list. It's not exhaustive list, so people may invent other reasons for looking at ghosts, and I will be happy to hear them. But basically, this would be what is my partial motivation if I have not forgotten anything. So now let me present what is our model. So let's start from very simple things. So we looked, I'm a simple-minded guy. Let's try to take mechanical model to begin with. What is the simplest option to look at some ghosts interacting with normal guys? So let's take normal Hamiltonian of normal oscillator for simplicity with frequency 1 and mass 1. Well, there you write another normal oscillator, which is almost normal because it has the wrong sign there. And that's why it's a ghost oscillator. So if they don't interact, this system is stable. We don't care about anything. So it's all fine and beautiful. But of course, that's not what we're interested in. We're interested if there is an interaction potential. Namely, this guy VI. And here, of course, we introduce simplest interaction, namely potential one, without momentum. And so it's basically the simplest model which one could have. What is not simple there is the following, that we actually assume this form of potential, where lambda is a coupling constant. So as you see, one could say that the form of this potential is a bit bizarre. Well, it's not polynomial, and moreover, this potential is actually chosen in such a way that this interaction is always bounded. Okay, so basically, you could think that this coupling constant is whatever you like. Generically, you would probably think that it's better to have it less than 1. But the very form of this potential is such that even if you go to large values of your coordinates in phase, whatever, if you want in phase space or in configuration space, so nevertheless, this interaction is always bounded. So it never can be really, really huge. So this is what I mean, it's not usually the case, because usually, of course, we would like to have, let's say, quartic interaction, let's say x squared, y squared, or higher order interactions. But we choose this one, and you will see from which reasons. Because, of course, our goal was to construct an example which would be stable and nevertheless interacting. So what is important, it's very easy to see in this representation of this potential is bounded because it's basically 1 divided by square root of 1 plus something positive definite, okay? So in reality, you can write this potential in a bit simpler way, just it's less obvious that it's always less than 1 in that presentation. And if we take now total potential, so namely we take this interaction potential plus quadratic parts of ghost and non-ghost potential, the total potential actually has this form if your modulus of the coupling constant less than 1/2. So it looks like a nice saddle, or it has slightly more complicated form with actually 2 saddles if your coupling constant by absolute value is larger than 1/2. So interestingly enough, if you expand around 0, then you get, of course, this interaction introduces corrections to your frequencies. So you started from 2 oscillators of frequency 1. Now these frequencies got corrected. So the frequency of normal oscillator got additional piece related to lambda with negative sign, and the frequency of ghost got this piece related to the interaction constant with positive sign. Importantly, our quartic coupling constants, as you see, they're kind of fine-tuned in the sense that quartic self-interaction is the same as the mixed term, okay? So it's basically the same lambda, or okay, if you want, there's this factor 4 in cross term. So what is very important is, as it turns out, that contrary to normal potentials with normal positive definite degrees of freedom, the origin for small coupling constants is actually stable, even though it's a saddle point for the potential. And one can then also show that the 2 saddle points of this potential for larger coupling constants, they're also stable. But that's what we are not going to show, because I would be more interested in more natural case of small coupling constants. So basically the statement is the stable motion is not at the minimum, but actually at the saddle point of the potential. And this is highly non-trivial because you see, so very naively, you look at this expression for linearized potential around 0, and you could say, okay, what's the point? So lambda is less than 1/2. Why cannot I use what is probably, we all have forgotten how it's called, but it's called Lagrange-Dirichlet theorem, which basically says you that a mechanical system is stable at the minimum of the potential. But here the important thing is that in reality, the key point of ghost instability is that it happens due to interaction, so it's purely nonlinear effect. And the statement that the system is stable at the minimum is actually a statement about asymptotic stability. And it's a statement when your energy dense, basically kinetic energy is positive definite. So here it's not the case. So if you want, it's a counter, or if you want generalization of this Lagrange-Dirichlet theorem for this particular system. Okay, so in the next, we are going to basically linear approximation here to show stability is not enough. That's what I wanted to say. And what we are going to deal in the next slides is related actually to this case. Okay, the one which is more natural, where the coupling constant is less than 1/2 by absolute value. Okay, so now what are our numerical solutions? Because look, we are dealing with mechanics, it's super simple. Let's look how, for example, x and y would behave if we deviate from our saddle point. And as you see, our deviation is not small, it's we moved away. So the amplitude in x is 2, roughly speaking, 2.4, and in y is 1.2. And what we see looks like normal oscillations, superimposed over each other. We looked at it at, like, let's say, just in this picture, it's hundreds already of oscillations, and there is no sign of any instability. But of course, one should be precautious because, these are particular initial data, we use particular numerical method, and on top of that, we don't know what is the rate of this instability we should expect. So it may happen that because it's nonlinear systems, this instability would intervene later and something else would happen. So also it's nice to see how the projection of these trajectories look like, not in xt extended space or yt, but just in ypy space. And it looks like it's almost like a projection of some tori, right? And here the time goes from red to blue. And as you see, it's pretty non-trivial picture. And even more non-trivial is a picture of what would be the analog of the Lissajous figure. And if you, of course, you don't remember what it is, at least I would not. It's usually a picture on a oscillograph, and when people do radars and so on, it's basically superimposed oscillations in 2 dimensions, but usually it's normal oscillations. It's 2 normal decoupled oscillators. Here, these oscillators are actually coupled. Moreover, one of them is a ghost, but nevertheless, we can create picture a la Lissajous. And as you see, it looks like a nice pillow, and the time goes up to this 500. And of course, naturally, you can expect that if you wait longer, the trajectories would just cover it's more and more dense fashion, but they would not leave through the borders of this pillow. Okay, but you see, even before us, there were examples of systems which were stable in the sense that people analyze them numerically, and they could see, okay, it looks fine, especially mechanical systems. But the question is, can we really show it analytically or not? So basically, again, numerical solutions look pretty stable, but it doesn't prove anything, because for us, what's interesting are to show it for all initial data and for arbitrary long times. And however, these numerical examples show it that maybe it's actually a stable system, right? And then again, so we are interested in analytical proof, because why should we trust the numerics? Okay, so now we can go and see, so what is our key point in being able to show it analytically? So in reality, this system is very, very particular. So that's why we have chosen this ugly potential. So namely, we can use the power of imagination in both senses, or whatever, maybe in 3 senses. And the point is the following, that actually this system has this first integral, okay? So in reality, this mechanical system is an integrable system. And it's kind of highly non-trivial, because I don't know what is the underlying symmetry. I mean, algebra one could build, but like really symmetry of global transformations in this phase space, which would give me such a conserved quantity. And also interesting is that it involves also this generator for hyperbolic rotations. So you see, if the sign in this K would be minus, we would recognize, of course, normal rotational momentum, Z component of rotational momentum. But here the sign is plus, okay? It's connected to the point that one of these guys is actually a ghost. So actually this was obtained, so was a system which we have analyzed, obtained through some canonical transformations, and before that complex canonical transformation from another system, so system with tildes. And this system was introduced or derived, if you want, by Darboux in 1901. And basically, he wanted to find systems with quadratic kinetic terms, of course, with proper sign, such that they would be integrable, without any basically further, motivation of physical applications. So for him, it was important to see that there are such integrable systems. And then he derived actually many of them. We analyzed some subclasses, and we found that if you do complex canonical transformation, if you want this power of imagination, then you can switch the sign of the kinetic term to get a ghost. And nevertheless, the system in this new variables is real, and the integral of motion is actually also real. Okay, but of course, it's the point that the integral of motion is conserved, is preserved under such complex canonical transformations. In reality, we had also to do some other transformations on top of that, but that's not that relevant here. So symmetry, I don't know. So if people are mathematically minded, it would be very nice to understand what is exactly the symmetry behind this. And this is the key point, because this integral of motion C is not that useful, but you can create another first integral, namely E, or curly E. And this is nothing else as the difference between the C and the Hamiltonian. Not that the Hamiltonian was conserved, C was conserved, so therefore E is conserved as well. And this E looks nicer from the following perspectives, that actually it contains the sigma, and the sigma contains integrals of motion, which are basically the absolute value of energies for both subsystems, plus this analog of the rotational momentum squared. So if you want the rotational energy. So basically this sigma is the sum of three integrals of motion, which would be there if the system were not interacting. However, somehow this integral of motion gets preserved, not preserved, but if you want, extended by this interaction, by this term y squared minus x squared multiplied with this unpleasant interaction potential. So the cool point about that is the following, that as this interaction part was bounded, you can see that actually this part of this first integral is bounded as well. So it always lies between the absolute values of the coupling constant. So it's larger than the minus absolute value of the coupling constant, and it's smaller than the positive value of the coupling constant. And this is very easy to see just if you look at this form of this potential invoking immediately, like this 1 plus something positive there. So the key point is that due to this boundedness of this interaction part of the first integral, for all times, this first integral E lies in a band between this sigma minus lambda and sigma plus lambda. Okay, put either think that lambda is positive or put absolute values there. And this is very important because this is the key point, namely, as you can see. So let's take some initial moment of time, TA. In that case, at the initial moment of time, this integral of motion lies between these two values. Take later moment of time. Of course, you could choose even earlier moment of time, but that doesn't matter. Take later moment of time. Again, the integral of motion is the same, and it lies now between new values, namely this sigma, but at moment B minus lambda, and sigma at the moment B plus lambda. So now what you can do, but the E is the same, so therefore you can say that sigma A minus lambda is always less than sigma B plus lambda. And on the other hand, sigma B minus lambda is always less than sigma A plus lambda. So therefore, what you obtain is that this sigma B is actually confined in this stripe, as you can see. So now this is very, very, very important, right? Because this stripe structure was seen already in this phase space picture. And then next thing what you can see is that because this trajectory is confined there, you take a vector in this four-dimensional phase space, and you see that this vector is less by absolute value than the square root of 2 sigma. And therefore, the system always actually evolves in a finite region of phase space. So you start from somewhere, you can never leave this stripe at all. So you see, this is pretty non-standard because it's a global result. So it doesn't matter where you start, you never go to infinite values of your neither momenta, no coordinates. You always stay in the neighborhood actually of your original surface given by a given value of this sigma B, if you want. Well, on top of that, we wanted to be more mathematically precise, and in reality, we also wanted to show the stability, or namely Lyapunov stability of the origin. So namely this integral of motion in this form which I wrote just for you not to forget, because you see it's all very elementary, so therefore I'm going to such a detail. So the point is that this E at the origin is just 0, manifestly, that's crystal clear. On top of that, if you take lambda product with this y squared minus x squared, so basically you're in such part of configuration space or phase space where this is larger than 0, of course, clearly sigma is positive definite. And therefore, this E in this part of the phase space is always positive, okay, if you exclude the origin. On the other hand, if you take this part to be negative, then you could say that, okay, because the interaction potential was bounded, then at least this E is larger than the most negative thing, which could be there, so namely then the sigma plus this negative guy. But if you look how it looks like, you would reproduce the energy of rotations, this or whatever, hyperbolic rotations, this k squared, plus the absolute values of both Hamiltonians, okay? Because as you can recognize, this is p squared plus omega squared x squared, so it's both Hamiltonians in linear approximation around 0. Losha, I think, raised a hand. So Losha, what did you want to ask? By the way, I cannot...
Don't worry.
Sorry?
I will ask after you talk, don't worry.
Ah, perfect, perfect, perfect. So basically, you see, the point is that by doing that, we see that in the whole phase space, this first integral, or if you want, this function on phase space E is it's conserved, so its derivative on the phase flow is 0, at the origin is 0, and it's positive definite. So basically, of course, positive definite for lambda by modulus less than 1/2. So basically what you see is that this E is a Lyapunov function, and by the second method of stability introduced by Lyapunov when he was actually working in Kharkov University in 1892, he can show that the system is stable. So basically this system is Lyapunov stable, and Lyapunov stability is one of the most strict requirements for definitions of stability which you can invoke. But there is interesting detail, probably Losha knows it, but Losha used to work in this Stiklov Mathematical Institute of the Russian Academy of Science, and Stiklov was a student of Lyapunov. And Stiklov also studied in Kharkov. That's just historical remark. Probably you guys don't know where the city is. Okay, so finally talking back to higher derivatives and so on. So what is really funny is that you can obtain such a system with ghosts through a bit ugly, but nevertheless constructible Lagrangian. So namely, you write a Lagrangian which depends on higher derivatives. It does not depend on first derivative, only on the second. And you need to invoke here as this P2 a solution of this a bit ugly equation. And that, together with some very simple linear canonical transformation, would allow you to construct, following the prescription of Ostrogradsky, would allow you to construct such a theory with the Hamiltonian I looked at before. So basically, it's a bit even more ugly than this interaction potential, but the price for it, okay, it's manifestly okay. That's your Lagrangian. It's non-degenerate. It has high derivative terms, high derivative equations of motion, 2 degrees of freedom. One of them is ghosts. They interact, and it's all stable, as we just have proven before. In reality, you can also prove stability of other solutions. It's just more involved because you would need to go to more involved analysis of these Lyapunov functions, but it's possible. So, but to prove that the origin is stable, and then by continuity, actually, it would imply that solutions close to origin are stable as well. So another thing, by the way, what I wanted to mention is that we could show the stability of the origin for this absolute value of lambda less than 1/2. But the statement that the motion is always happening in a confined region of phase space, so there's no runaway, this applies for arbitrary values of lambda. Because the lambda is big, small, less than, doesn't matter. So it's for all lambdas. Okay, so basically now I am slowly converging. So basically my major question is now the following. Why have not we seen such systems so far in nature? Okay, so basically it's not stability which precludes their existence. Moreover, one could say, oh, maybe it's super duper fine-tuned and this potential is kind of bad. But on the other hand, following Kolmogorov-Arnold-Moser theorem, one could introduce small structural perturbations into this Hamiltonian. So basically add other terms, assume that these terms are smaller than the interaction term we have. In particular, by the way, that would forbid you from having unbounded interactions. But then you could say that they are definitely their system is stable again, and due to the Kolmogorov-Arnold-Moser theorem, that the motion is finite and so on. So I'm really curious, why don't we see them? So thanks a lot for your attention.
Okay, Alexander, can you hear me? Because I tried to speak before.
Yeah. Now I can, but before that I could not.
Oh, well, anyway, it was perfect because we're on time and everything. Thanks a lot for the talk. So there was the question by Alex, who raised his hand before, so I guess he has priority. Go ahead.
Okay, thank you. Look, I have a question because I tried to understand what you are saying, and I got an impression that your construction is very much fine-tuned in a sense that, of course, it's very much great classically, but I don't understand. Do you have an idea how will it work at quantum level?
Very good question. Look, I think actually it will be all fine also in quantum level, and I can tell you why. Because it's actually perfect question what you asked, because there were many works where people would analyze similar mechanical systems numerically, and they would see that there are no instabilities. Either no instabilities at all, or as it was done in recent papers by Damour and Smilga, they would see instabilities which are kind of mild, and for them, basically, if the system does not run in a singularity at finite time, they will say, okay, it's a benign instability, which is actually kind of legitimate point of view, because you could say, okay, our universe is expanding, and that's in a sense an instability.
I mean,
but,
what do you not universe actually, and classical stability doesn't guarantee quantum stability.
Absolutely. But let me go to the detail what I wanted to answer. In particular, if you look at the system with quartic interaction between ghost and non-ghost, let's say lambda x squared y squared.
Yes.
For small lambda and small values of x and y, this thing looks numerically perfectly stable. But exactly what you are saying, wave functions you cannot localize completely. So basically, they will always, even exponentially, even very tiny, but they will probe the region with x and y such that this interaction terms, basically, if you think about superposition, imagine you superimpose classical motion and you probe always such part of your phase space, or if you want configuration space, when the whole thing runs astray. So in that sense, it is true that classical stability doesn't imply quantum, because these systems quantum mechanically would be bad. In our case, what gives us a hope that that would be okay quantum mechanically is the following statement, that if you want, it's twofold statement. So one statement is that there is no runaway everywhere in phase space. And therefore, even if your wave function is distributed and probes as far as you want, you never run away. You're kind of confined. It's one argument. And second argument is the following. Imagine you want to look at basically eigenstates or stationary states. In that case, you have two integrals of motion, your energy and your whatever, E or C. And the whole Hilbert space can be enumerated by the values of this H and E, because they commute. And one of them is bounded. You see, that's the interesting thing. So one of them is positive definite.
Actually, this was related to the second part of my question. Can you return to the slide where you write explicitly the potential? Is it possible?
Yeah. Okay, let me, because I read it in some slides. For example, maybe it's, maybe it's better to see it here. Yes, that's the potential.
Yeah, so definitely you kind of playing a game which is known in the mechanical system as the hyperbolic billiard system. And I'm kind of confident in what I'm speaking about it because it was part of my PhD thesis. It's in some regime it's stable, it's okay, and regular. In some regime it's chaotic, in which you will have great difficulty to define whatever you speak about.
Look, I would be extremely happy to discuss it. Sorry, your connection got broken.
No, I'm saying I'm not sure how you will proceed with all of this in generic situation because I mean, it's not very well defined. I mean, it's a well-defined system in a sense that you have to define which state you consider a regular or chaotic one.
Wait. But you see, this is a statement which probably my education is not enough because it's an integrable system. And whether the integrable system can be in the same way chaotic, I doubt. So it's completely integrable model. In a sense, so it's similar to this hyperbolic billiards, but it's not identical.
It's not identical, but it can be. The system is integrable and chaotic. It's no contradiction about this. The question is whether it's stable or not. Chaotic means stable or not integrable.
Well, this system is stable. You see, that's the point. Because we have an analytic proof for that it's stable.
For any lambda?
No, for lambdas less than 1/2 by absolute value.
Okay.
That's for sure.
So it means essentially that if you're going to quantize a system, you should be sure that your quantum states and quantum behavior will not lead you to behavior equivalent to something of lambda other than in the domain which you have specified.
Well, but we are doing quantum mechanics. In quantum mechanics, this lambda is fixed, right? It's not quantum field series. There's no running or anything.
Yes, this I agree. Yeah.
So formally speaking, there we are on a safe space.
It's curious.
But you see, the interesting thing is that if had we required that lambda should be almost 0, in that case, we could again use Kolmogorov-Arnold-Moser because without lambda, basically without this interaction, this is also integrable system. Right? Even though there is some assumption of finiteness of phase space, which would be violated by this wrong sign, but one could try to avoid it. But you see here, lambda is even 1/2, okay, 1/3 or whatever, and then it works.
I see. Okay, interesting.
All right.
Indeed.
Okay, so we have at least 4 more questions. So I think
perfect.
So in the order that I saw them, there's Philip first, then Alberto, then Alessio, and then Ilya.
Okay. All right.
Yeah, I get. Okay, as you wish. Okay, so let's start with Philip then.
Okay, Alex. Hello, nice to meet up with you again.
Yeah, indeed. Me too.
I have a terminological question and then a physics question. Why do you refer to negative energies as ghosts rather than negative norms? I mean, you can certainly say having negative energies is a disease. Yes.
Yes, but you see, that's exactly the point. So I want to be as standard as possible. So in a sense, and I'm doing purely classical mechanics, right? So therefore, here I cannot introduce any other norms, right? So I know what is my energy, and it is what it is. And actually, had I tried to say that this energy is positive definite, I would need to do this canonical power of imagination, this imaginary canonical transformation back. But you see, the interesting thing is, basically, I don't know whether I would be able then to claim any stability even for this sign. Probably I would, but that's a different story.
Okay, so anyway, that was the terminological question. Now the physics question. If you just deal with 4th order gravity with an Ostrogradsky instability, there's also a problem of negative norms as well as negative energies, but they're in different Hilbert spaces. So you only have to solve one. Now, if you stay with the Ostrogradsky, not only do you get negative energies, but if you quantize the system, the wave functions are not normalizable. Now, if I look at your model, if I were to replace y by iy and py by minus ipy, I would not change the commutation relations. V1 of x and y is invariant under y goes to iy. But then I have a Hamiltonian with a plus sign where you've got the red minus sign. And that one for sure, the wave functions are standard. So the question that, and I think Alexei was asking the same question, if I now continue back to where you are, would the wave functions remain normalizable?
So you see, the point is,
because it looks like they may not.
So you see, that's a good question. But for us, this complex or imaginary canonical transformation was purely a way to obtain the resulting system, right? We do not want to deal with that after that, right? So let's quantize what we obtained, right? Because this is the system at hand. Otherwise, we would need to say that our observables are not Hermitian but anti-Hermitian.
Yes,
we
exactly.
don't want it.
Yes,
here we don't want it.
No, that was the point. The point is that if the observables were anti-Hermitian,
yes,
the Hamiltonian is manifestly stable.
Yeah, absolutely. But you see, that's exactly what we want to avoid. We want to say that let's be as standard as possible, forget how we got this system, right? And just imagine somebody just gave you this Hamiltonian and you worked with this. Okay. And basically in this way, so the only way to find the Hilbert space is to look at eigenvectors which are enumerated by eigenvalues of both H and this E. And then E is bounded. So therefore, in reality, think of the following way, you would not even know what is H and what is E in practice. So therefore, you could say that actually this whole thing has Hamiltonian, so to say, Hamiltonian E. And this was positive definite. So therefore, the whole, so to say, motion, which is in finite ratio phase space, implies that their wave functions will be normalizable. They never leak infinitely. What would be the case in non-normalizable states?
Yeah. Can you show me the C operator once again? You see your
C. C means the C classical. Let me show you E because C, you know, it's what Cartan wrote with up to some sign.
Okay.
We wanted to have E.
No, go back. Go back. You had it on the previous page.
Okay.
You just went,
so this one is already now a signature. This is after transformation, not before.
Yeah. But you see, this C does change sign if you make Y anti-Hermitian.
Well,
your argument is now you solve the theory that you want under this constraint that C is time independent. It's a very special class of solution, which is okay.
No, it's not. No. That's exactly the point. It's not constraint. It is a result of the dynamics. That's the point. It's a conserved quantity.
Oh, it's a first integral. Yes.
It's a first integral. Exactly. That's why I need to, that's why basically when formulating Hilbert space, I will need to solve simultaneously system of equations. If I want to look for stationary states, it's H psi is equal E psi, and then this curly E or whatever C psi is whatever eigenvalue of this guy psi, and they commute. That's an important thing because it's an integral of motion.
Okay, so what happens is this integral of the motion is not invariant if you replace Y by IY.
It's not invariant. No.
Even though the original equation was. I mean, the original equation was not, but the VI
was not. They're never invariant. You see, that's the point.
I'm sorry, I didn't mean invariant.
Yeah.
So this function changes.
Yes.
If Y, so maybe that's the answer.
Yeah. That's the answer. They do change. That's a very interesting thing. So you see, in reality, we entertain this exercise also for Kepler problem, which is integrable. And there, if you go to basically this imaginary, so to say, phase, if you look at everything in complex space and you look at just imaginary, so to say, direction, the motion goes straight. So basically finite time singularities, that's what happens there.
Okay.
So basically just the presence of integral of motion doesn't guarantee you any instability. And even if in the real part it's stable, in the imaginary part is not. So this is very subtle. We were looking a lot for different systems derived by Darboux and company to see which one of them would allow us to have the finite motion. And that was not a trivial part of the job.
Good. Good.
All right.
Thanks.
I think in the discussion session with the remaining 2 questions for this talk, and then the discussion can keep going, involving all speakers of the day. So let's say we're officially in the discussion session. That we have immediate questions by Alberto and Alessia. So let's go with Alberto.
Okay, thank you. Thank you for your nice talk. So I have a comment and a question. The comment is that I think that the runaway time in general can also be larger than the age of the universe. So it's also interesting to analyze systems that are not strictly stable, but can be, metastable in the sense that the runaway time is larger than the age of the universe. Like, for example, the Higgs potential in the standard model. This is the case for M top around 173 GeV. So
Agree.
we are probably in this situation. So it's also interesting to allow the runaway time to be larger than the age of the universe. And then the question is, so there is another paper. I don't know if you know. The question is if you know this paper. There's a paper by Gross, Strumia, Teresi, and Zirilli that was published in 2020 that also claimed to have proved analytically the stability of ghost-like systems. Let's say
that's
mechanics.
Not that I were. Alberto, if you can send me the link, that's to my shame. I am not aware of. But
I can
what
say,
they have a particular example, or it's some more general setup?
It's well, it's always examples. It's not completely general. There are many examples in the paper, so not just one.
So it's gross.
I can send you the link now to everybody in the chat.
Yeah, would be great. Would be great because I'm not aware of this work.
I've just sent the link in the chat.
Perfect.
And so in this paper, by the way, they also give examples of physical systems with ghosts. That what you were looking for, what you were looking for in the slide, if I remember correctly.
Okay, let me see. I'm just opening it now. And okay, the explore possibility systems with negative kinetic can be metastable. Metastable. They say metastable?
No. They show that some systems are like they have runaway time bigger than the age of the universe, but they also show I think analytically that some mechanical systems are completely stable if the coupling constant is small enough.
Wait,
that's an example. So.
Yeah, now I'm looking at it. Okay, well, because you see, to my shame, I didn't know about this paper. I'm now looking at it. So I know that in some cases, people would just decouple both degrees of freedom, and then it's all fine. And then, yeah, so they, that's a relevant paper, but okay, I'm just trying to, do you know at which page should I actually look at?
For the mechanical systems, you mean?
Yeah, I see many mechanical, but so far I see either unstable or those with metastable behavior, which takes just very long time.
I think it's section 2, and also they give physical examples. Like asteroids around the Lagrangian point in Appendix A.
But wait, asteroids can have negative kinetic terms. That would be quite unusual, I would say, no?
And that is a mechanical system. If you look at the Lagrangian.
Okay. Well, what I see is this 56. This is well-known example, right? So there you see that this system would be stable for small small coordinates. That's for sure the case. But if you go to larger coordinates, it all goes to run away. So therefore, I don't know. Look, I need to read it. I never read it, so it's pretty interesting. But
so you're saying, okay, so this is possible that maybe they don't have an example of a system that is stable for any initial condition. So
yes, this is exactly the key point.
That's possible. I'm not sure. Maybe they also prove that in some cases, but I'm not sure.
Yeah, well, could be, because you see, I'm now scrolling it to the first time. So sorry, it seems that I completely missed it, even though I always try to catch up with such things. But okay, look, it looks like very relevant. It's pretty bad that we were not aware of this before. What can I say? But yeah, so at least in the abstract, I don't see that they would say that they have proper example which would be stable everywhere.
Yeah, that's possible. Yeah.
But okay, look, it's long papers and pretty relevant.
Read it carefully. But
yeah, I will. Of course, I will. But thanks a lot for pointing it out. That's pretty interesting.
Mm-hmm. Okay, thank you.
Well, thank you.
Okay, so Ivano is not here. So quickly, I will ask my question. So first, thanks for the very interesting talk. My question is just very simple. I think I did not really get what exactly fails in the Ostrogradski theorem. Because I mean, as you mentioned, there are certain assumptions. So, for instance, that your system is not non-degenerate or non-degenerate, and other assumptions. And in that case, you would have linear instability. And since you don't find any instability, I'm wondering what exactly, which assumption exactly you are violating in the Ostrogradski theorem, or what goes wrong in general?
Well, because Ostrogradski theorem, you see, the point is, there is an assumption in Ostrogradski theory. Well, okay, it's not actually Ostrogradski. You know, the funny thing is, Ostrogradski didn't even know about works of the Hamilton, and he was deriving this Hamilton on himself. And the point is, he never read in English, but he was reading and writing in the Russian and French. That's just a side remark. So basically, he was not aware that he's deriving Hamiltonian mechanics at all. The point is that that there is an instability due to this linear term in momentum in your Hamiltonian was raised much later, partially by Richard Woodard and partially before that even by Pais and Uhlenbeck. I think Pais and Uhlenbeck were probably the first who paid a lot of attention that systems with this high derivative should be unstable. So now what goes, so to say, not wrong in, so to say, Ostrogradski construction. So we can use Ostrogradski construction, not a problem. But what goes opposite to normal expectation? Opposite is the existence of this integral of motion, which is positive definite. And if you want, this integral of motion binds your motion in a given region of phase space. It doesn't allow you to escape. It's a trap. In the same way as positive energy is a trap, it doesn't allow you to go away. The same way is this integral of motion. In reality, the interesting part is that we had to use this integral of motion just to prove the stability analytically. But I bet you there are other systems without integrals of, I mean, at least time and like proper integrals of motion, which can be also stable. Moreover, I can tell you that what I'm definitely aware of, there could be systems with time-dependent integrals of motion if these integrals of motion are nevertheless positive definite, they also trap you. And then this argument that you can exploit the unboundedness of your Hamiltonian doesn't work because you would need, basically, you would be confined by something else. So that's what goes wrong in Ostrogradski procedure there. So basically, there's different ways to exploit it. So either you create degenerate dynamics, or it's a gauge system, which also means that it's degenerate. Or in some cases, you may have conserved quantities, so that basically it's true that you can pick up this original momentum as low as you want, but after that it stays the same. Doesn't matter how you interact. That's another, by the way, option. And here we have a different option that basically there is a conserved quantity on top of energy, and that binds you. That doesn't allow you to escape. So that's a key thing.
I see. Interesting. Thanks.
Thanks. By the way, I see also some something in the chart, and then there is some other paper. Oh no, that's the same paper.
Yeah, there were some papers linked. Yeah.
And by the way, yes, just give me a sec.
So meanwhile, can we proceed with the discussion, or?
Sure.
All right, so I remember there being a question by Luca for Philip, right? Yes. Okay, I think this is the right time. Go ahead.
Shall we stop the screen sharing?
Ah, well, I don't know. Do you need Philip's slides?
No, just to see Philip, because I don't see him.
Probably I should stop sharing, yeah, guys.
I think it's better.
Okay.
All right.
Maybe actually here we are proposing, some people are proposing a break. Maybe it's good to stop for 5 minutes and we start again. Is it okay? Yeah.
Okay. Guys, at some moment I will need to leave because we have also a visitor and I will need to disappear. Sorry about that. I wish I was there with you, but next time.
Anyway, very nice.
I'll answer your questions.
Sure. Maybe we can wait just 5 minutes. Just 5 minutes break and we meet again. Okay.
Maybe I have a question for Alex.
Oh, very good.
You can keep discussing it.
Sure, of course.
Yeah. Break.
So Philip, I don't hear you.
No, I don't have a question for you. I did already. I just wanted to know if anybody else did.
Sorry, what?
I just wanted to know if anybody else had a question for you
okay.
before you were about to leave.
Well, I can stay for next, I don't know, probably 10-15 minutes, and then I would need to disappear. And sorry, guys, today we had some basically talks at the institute, so I had to basically be.
No, I believe we will recombine. You see, the local people, they need some break a little bit. They in one room. It's a little bit like anomalous that I'm again not there, but most, at least 10 or 12 people gathered in Portugal now.
Wow, this is an achievement, like now it's all in person again, so that's fantastic. Losha, where are you, by the way, now?
I had to return to Brussels because of some accident, but anyway.
Oh, okay. But you're fine, right? So you're okay.
Yeah, okay. It's not so bad, but it's fine.
Okay.
Let's put it like okay. Compared to many people around the globe now, I mean, I'm feeling like really good.
Look, unfortunately, this thing is unbounded from below, like that's the problem.
Yeah.
It's pointless to compare, because some people are always suffering much more than you.
Yeah. This I agree.
All right, let me switch on light.
But actually continuing discussing a little bit, what I was starting to say, I have put quite a big deal of time to discuss these hyperbolic billiard systems, and how can you avoid chaotic behavior there? But even if you do, I'm still a bit suspicious about quantization of your system, really. I mean, well, it's still possible, of course. I mean, I don't mind that you can do some procedure, but it deserves some extra attention. This is at least.
No, I agree. But you see, for us, main reason to find that it's everywhere in configuration space does not allow you for runaway was very important exactly from this perspective, to find basically that these wave functions never, so to say, they never leak out. You know, they use very simple, if you want, so to say, many world interpretation. So if you think you have normal Heisenberg equations of motion, which is identical to classical equations of motion, of course, here orderly problems could appear, but okay, let's neglect them for a sec. And then if you have standard Heisenberg equations of motion, the wave function would just tell you the distribution of initial data. But you see, if for each of the set of initial data, doesn't matter with which probability you are there, you kind of stay then in the stripe, then this wave function will not go astray, will not expand. So therefore, in this perspective, it's kind of clear that at least naively clear, that it should be okay. You see, I'm afraid that to write proper quantization, one should do it numerically, which would be basically not that nice, because one would need to solve a system of Schrodinger equations. Or if you want Schrodinger-like equations.
Yeah, this is right. It's not like straightforward thinking.
Yeah. And I think analytically it would be not that easy.
At least exactly about x squared, y squared potential, it was a lot of papers by these Russian guys, exactly Medvedev, if you know this.
I actually don't. That's very interesting.
I can send you some links. I don't remember now by heart, of course, but I can send you links.
Oh, perfect. That would be very helpful.
It was, in fact, papers by Medvedev and Polivanov and guys like this. I was reading them a little bit, not too much of attention to be true, but okay, well, spend some time. No, because you see, when I was doing some study about the zero brains or whatever, it was exactly x squared, y squared potential, kind of exact. So, but now you are presenting somewhat more difficult. And there's study about this. And actually, it was related to this zero brain business, you know, when people were dimensionally truncating young mills from d+1 to 0+1 dimensions, they were obtaining stuff like that. Because when you have d+1 dimension young mills and reduce it to 0+1, what you get from quartic interaction, you get this exactly quartic potential for your coordinates. People were studying it a lot. I mean, it was some great activity, at least the time when this BFSS model was popular.
By the way, as far as I remember, this quartic coupling and it's exactly the chaotic one, right?
Yes, chaotic is, well, it's not exactly chaotic. It has some kind of, there is no strictly speaking stable phase, but in some regime you can observe for a very long time stable motion, which obeys all the rules of stable phase, etc. But then you should anyway somehow enter chaotic regime.
Yeah, that's what was not clear, because I don't know whether Philip knows this work or not. There was a paper by Alex Kovner and his collaborator Lubinsky, I think. And they were looking, sorry?
Alex is in the office next to me.
Perfect. Yeah. And I think they were pointing out that with this quartic coupling constant, there could be, at least numerically, it looks like stable. Moreover, Mark Troden and Sean Carroll and I have forgotten who else was there. Maybe, whatever, doesn't matter, basically. These two guys and somebody else, when they were discussing energy conditions, they also had this discussion of this quartic term, and they numerically saw that it's stable, kind of. But you know, the point is, you can never trust the numerics because you don't know. Okay, finally, it's clear that close to this initial data, it's stable, because otherwise it would go astray numerically immediately. But you don't know for how long do you need to wait, because there is no proper estimation of this numerical, of this nonlinear instability. Therefore, it's very hard to say, like, okay, now it's stable, but then maybe after that, there will be an instability, and this instability may even increase the rate stronger. So that's that was always a equation.
No, but actually you have some techniques how you can judge whether stable or not. But it was proven that for x squared, y squared, potentially it is generically always chaotic. And it was also a paper like if you, for example, consider some linear addition to it, like minus x or minus y, so that it, or minus x squared without x squared, y squared, it goes to be like stable. So this kind of possibility to kind of make this plane a bit inclined to some direction by this linear contribution, it makes it stabilized a little bit. A little bit means that you can propose some phase transition between stable and chaotic phase. Well, I even can refer you to one of my papers where it was studied, one of the earliest.
No, would be cool. Please send me a link.
I can send you the exact reference how it was worked out. But what I remember, because it was indeed quite 25 years ago, it's not like you can easily claim that system is stable or chaotic. You need it evolves, it looks like by all characteristics like stable, for example, but you cannot say that it is stable by strict demands of dynamical system, whatever.
Interesting, because you see, here it's like literally Lyapunov's second method of stability.
No, there also you can say like Lyapunov exponent is whatever, small or whatever, but you cannot prove actually that it's gonna to be like that for all over the time forever.
But here you can, you see that.
Okay, this is different. Yes.
Yeah.
But
and that's the mystic of the system.
Potential. So no, I don't mind that your system may be totally stable. I just bother about what bothers me if you're gonna to quantize it, having states which manifestly have negative energy. This kind of drawing some concern to me.
Believe me, for us too. But from the point of view of the second integral of motion, this sort of say would be energy. It's okay. So that's fine, because you see, they would restrict you from doing it. That's the point. So think in the following way, that look, the only way why do we care about energy is because there are many different systems and all of them conserve energy. So here, if you take this thing in isolation, then you have this integral of motion and you are happy to look at it, and then it can play the same role as energy. But it's not additive, because if you take another system, then this thing is not an energy anymore. So this could be interesting from the point of view of doing thermodynamics of this stuff, but I don't know. And you see, the thing is, it's kind of hard to say, because small interaction on top of normal integrability doesn't destroy the picture. And how to do proper thermodynamics, not in the basically in strong interaction regime, I don't know. Whether Luca has a question, I see.
Yeah. But Luca also has problem because
because he's muted.
He raised hand doesn't have microphone. I'm not sure he asked you. But anyway.
No, we cannot hear you.
We cannot hear you, Luca.
Raising hand doesn't guarantee to ask questions in this system, you see?
Hear me?
Yes, now
what I was saying is that I don't have a question for Alex, but for Philip. So if you want to it's okay, I don't know. Can I go or?
Of course, please.
Okay, so Philip, can you hear me well?
Yes.
Okay, so I don't have one question, actually, I have 3 or 4 questions. I hope I will be allowed by the chairman. So 2 of them are very quick. So the first one is basically what you basically consider is just conformal gravity in your talk, which is Vial square. And you try to make sense of the negative norm of the ghost, let's say, in this Vial square gravity. But can your prescription be used also in the case of stellar gravity, where you have R plus R square plus H square, and still give some unitary theory?
The answer is not only can it be, that's what Carl Bender and I did first.
Okay, good. Now
we first looked at second plus fourth.
Okay.
And then took the limit.
Okay, perfect. So at least in the talk, what you basically showed just was just the example of the Pay-Uhlenbeck oscillator.
Yes.
More explicitly. But I was wondering, in the case of gravity, of course, what you need to apply your prescription is to have an anti-Hermitian Hamiltonian, anti-linear Hamiltonian. Okay, and to do that, in the case of the four-order oscillator, what you were basically doing was, instead of having an X, you would have an IX. Okay, this IX would play the game then. In the case of gravity, I guess you would have some kind. You would need some kind of like I G mu.
Absolutely.
Okay.
Absolutely. So, can I explain to you why that's not a problem, despite the fact that it sounds like it is?
Okay, yeah, please, you can go ahead and then.
First of all, if G covariant mu nu is replaced by IG mu nu, then G contravariant is replaced by minus IG mu nu, because the product is a delta function. But that means that the connection stays real.
Yes, okay.
And the Riemann tensor is built out of the connection.
Mm-hmm.
So you actually are never sensitive to the phase of G mu nu from the gravity experiments that we've done. If you wanted to check, you'd have to do an interference with electromagnetism. And then the overall phase of the metric would come into play. But what you say is exactly correct.
Yeah, no, what I was also thinking, basically, let's suppose we take, so to have literally full strict renormalizability in the case of four derivative gravity, you also need a cosmological constant.
I'm not allowed a cosmological constant. It violates the conformal symmetry. I have to generate one by spontaneous breakdown.
No, but you said that, I mean, I'm just thinking about now the full action, like R squared plus H squared. If you want to renormalize that one, you also need a cosmological constant. Otherwise,
R plus R squared is renormalized.
Yes, I'm saying R plus R squared plus Y squared. Okay.
Yeah. R plus R squared without a cosmological constant.
No, I think you need cosmological constant to reach renormalizability.
Well, not. I don't think that was Stella's original result, but
no, he was just neglecting it for simplicity, but for the
but he got renormalizability without it.
You would generate also cosmological.
Let me say this: if you want to tell me that R plus R squared is not renormalizable unless you add on a cosmological constant, I don't mind, because I'm not doing R plus R squared.
Sure. No, what was
that's somebody else's problem. But what Carl Bender and I have shown is that R plus R squared doesn't have any states of negative norm.
Perfect.
Which is, and that's independent of whether or not there's a lambda.
Sure. Now, what I was had in mind now, like, let's suppose we take the full still Lagrange, where you also, I mean, up to my understanding, you also need a cosmological constant to really achieve renormalizability. And you write down the field equation in your theory. Of course, you would have a term which is basically mu nu lambda, where there is no curvature there. And once you send this G mu nu to I G mu nu, you would have a purely complex part of your field equation.
No. What's happening is this: the action would be R plus R squared plus lambda. The action's invariant under I goes to mine, under G mu nu goes to IG.
Okay, the action is invariant, yes.
So therefore, the equations of motion will be as well. I mean, there must be factors of I that fall out or that can cancel automatically, because it's a symmetry of the equations of motion.
Or without cosmological constant, maybe.
With a cosmological constant.
But if I think about the field equation, just with the G mu lambda.
Yes.
I don't see how this G mu.
I think what you're missing is this: the Riemann tensor doesn't change sign.
Sure.
But the Ricci tensor is one contraction of the Riemann tensor. So that would pick up a factor of I.
It doesn't have another metric.
But,
No, but you also have the metric determinant, right? Don't forget metric determinant in the measure.
No. The measure is due to the heart. The measure is the determinant of G mu nu,
Sure.
which is for G mu nu to the 4 is independent of the sign of I, because it's I to the 4, which is again +1. Anyway, I mean,
the field equations, that's where G mu nu comes in lambda, right?
Yeah.
Lambda G mu nu comes from variation of metric determinant.
yes, that's
So
right.
that's it.
Yes, but so does the R mu nu term come from the variation of the R to of the Ricci scalar. And the R mu nu.
No, but the R mu nu is different story, because R mu nu is function of inverse metric times metric, right? Times derivative of metric. And that's how they cancel out the I. Or not?
No. The I cancels in the Riemann tensor, and therefore the Ricci tensor picks up one extra factor of I.
Okay, I see.
Okay.
And that's why, if you now go back to the Bianchi identity, if the Ricci tensor picks up a factor of I, the Riemann scalar doesn't. The Ricci tensor doesn't. But the Bianchi identity is R mu nu minus G mu nu times R. And so the G mu nu picks up a factor of I.
Okay, maybe.
They must all, I just said the Bianchi identity is based on G mu nu, which is R mu nu minus a half G mu nu R. Now the difference between R and R mu nu is one extra factor of the metric. But then you've got another factor of the metric, which multiplies which is the G mu nu times R. So you can really write it as G mu nu lower, G alpha beta upper, R alpha beta lower. And then the G upper alpha beta and the G lower mu nu pick up an I and a minus sign, it cancels.
Okay.
Which it has to, because you can derive the Bianchi identity by varying the Einstein-Hilbert action. And the Einstein-Hilbert action is invariant under the replacement of the covariant G mu nu by I times G mu. It's just a little bit bizarre, but it's okay. I mean, it's not something that we've ever thought of because we never needed to think about it. But it is the case that when Carl and I start to do the quantization, you can ask the following question, which is, what's the condition on the measure of the path integral for which the path integral exists? And the answer is, for the fourth order theories, the path integral's got to go into the measure's got to go into the complex plane. But then the next question is, well, how does it do that and not change, or not make the path integral pure imaginary? And the answer is, the path integral is not really the path integral over G mu nu. It's the phase space, the integral over G mu nu and its conjugate. You have to start with the phase space integral. But then the conjugate will flip sign the same way the metric flips sign. So that picks up a factor of I or minus I. So that leaves you with a real path integral. In fact, I've written papers on this. The path integral should always be written, first of all, as the phase space integral. Now, in most cases, the integral over the momentum is trivial. And so you can just get down to the Feynman form where you only integrate over the position. But the correct prescription really is use the phase space integral. And for what I'm just discussing now, that becomes important.
Okay, I have actually one question, also a comment. Maybe first Benjamin Nor wants to
Yeah, sorry, it went a bit quick for me. I just want to confirm that I understood, because if you take the Ricci tensor, it's purely a function of the connection and the derivative of the connection. It does not involve extra metrics. And that's because the Riemann tensor, which is invariant under G goes to IG, has 3 lower indices and 1 upper index, and you contract an upper and a lower index, you don't get an extra metric. Do we agree on that?
All I was saying was that the Ricci tensor picks up a sign, a factor of I.
No, it does not.
Oh.
Because it's a derivative of the connection plus connection squared. There are no extra factors of the metric.
That's for the Riemann tensor, yes.
Also for the Ricci tensor, because the Ricci tensor is a contraction of the Riemann tensor of the one upper index, one of the lower index.
But it's a contraction with the metric.
No, it's a contraction with a delta.
Yes.
For the Riemann tensor, it depends on how you put the indices, right?
Yeah, exactly. It has to do with how one defines Riemann tensor.
So if you put all the indices down, then it picks up an I.
Yes.
If you put 3 indices down and 1 up, it doesn't.
Then there's no I, yes. Okay.
Yeah, but then I still don't understand the discussion on the equation of motion, because you get different factors from the cosmological term, because there's a G times lambda compared to the Ricci tensor term. So that's a different powers of I then.
Yes. Well, like I said, I mean, we have to do it more carefully, but as long as the action itself didn't change when you replaced G mu nu by IG mu nu, then the variation of the action with respect to G mu nu cannot change either. It can only have an overall factor of I.
But that's the point. The action does change because the Ricci scalar changes. So the cosmological constant term in the action does not change because it's just the measure.
Okay.
But then you have the Ricci scalar, and the Ricci scalar changes so under this transformation G goes to IG, the Ricci scalar should go to minus I times the Ricci scalar.
Okay, good. Then I'm happy, because I would therefore not have a cosmological constant to begin with.
Sorry, can I say something about this?
Yes.
But in your approach, you put an I in front of one canonical coordinate, not in front of both. So what you should
yes.
So what you should do is not to change G mu nu into I G mu nu.
Oh, thank you.
We have to split the metric into the graviton, the usual graviton, which is massless.
Yes.
And let's say the ghost. And then it's only the ghost that picks up an I. So it's not that G mu nu goes to I G mu nu, because that will be like replacing the full coordinate of the pi-Sullivan-Beck oscillator into IQ, but this is not what you do.
Thank you. Thank you. That's very good. But I'm looking at an action which is R squared. Yes, not R. And for R squared, it doesn't matter whether R picks up a factor of I or not. R squared doesn't.
So indeed, let's maybe
what Alberto said is correct. You have to reconstruct the theory in terms of the G mu nu, its first derivative, its second derivative, and third derivative, and then you construct the canonical conjugates, and then you make the transformation.
Okay, Philip, so if we can ask again. So what is the action of gravity that you are quantizing?
Well, I'm using C squared.
Okay, so
but you could use, but okay, let's back up. Let's make life a little bit. Yeah, I'm using C squared.
So it means that same prescription would not work if I have a term which is linear in a Ricci scalar.
That particular restriction would or would not wouldn't. I mean, the R squared term or the C squared term doesn't occur.
Sure. If you have term, I think now I agree. But if you have like Einstein-Hilbert term in the action, in the action, you cannot apply the same prescription by complexifying your.
I see what you mean. Okay, well, you can't. In that case, you can't do it in the Lagrangian. But what Alberto reminded us is you first of all have to. Because it's a constrained system, and you have to change the variables. And The reason why Carl and I were able to solve this problem is because it's a 2 oscillator theory, not a 1 oscillator theory. But it doesn't look like a 2 oscillator theory. It's because there's a constraint. After you've gotten rid of the constraint, at that point you continue one of the oscillators into the complex plane, but not the other. Now, one oscillator is probably going to be G, and its canonical conjugate is 2 derivatives of G, and the other one is going to be G dot, and its canonical conjugate is 3 derivatives of G. And so the way the canonical conjugate works is you go with two derivatives down. In other words, if you like, you're using X and X double dot, not X and X dot. And going 2 derivatives down would work.
So okay, let's take that.
But yes, we've worked it out. Now, it turns out that you can simplify the problem because, at least what I do, when I work with C-squared gravity on its own, I can find a gauge in which the equations of motion are diagonal in the indices. And therefore, I can treat each component of G mu nu as if it were just a scalar field. And then for the scalar field, I've worked the whole thing through the way I just described. And that's how I got all those commutation relations that I showed you in the talk. But anyway, yes, I mean, you might be correct that there are problems when we add in a cosmological constant. I mean, all that Carl and I were claiming is second plus fourth can still have, doesn't have to have negative norm states. So
now let's just focus on Vial square, and let's so assume that we quantize the theory like you did. So I can understand that in this way you might be able, you're able to solve the Gauss problem at quantum level. Okay, but it's not clear to me because I totally agree that to really describe classical physics, we should start from the quantum physics and then take correctly some classical limits. Okay.
Yeah.
In your case, Vial square gravity is your quantum Lagrangian for gravity. You quantize it with your prescription, yes. But then what would it be, your classical gravity theory? Because if I just take Vial square theory and I take the field equation, I know that the classical field equation should somehow have some instability.
Okay.
So, I mean, or also, where is my Einstein limit? Like Einstein-Hilbert?
No. I'm not going to get the Einstein limit.
Okay, so let's for now forget the Einstein limit. So how about this Ostrogars instability?
Oh, okay. Because once I've what I said before was, you can quantize the theory with either A annihilating the vacuum or A dagger annihilating the vacuum. You only get the Ostrogorsky if you make A dagger annihilate the vacuum, which you can understand. If A dagger annihilates the vacuum, it means that negative energy states propagate forward in time. And that means that the theory is unbounded from below. But I don't work in that Hilbert space. I work in the Hilbert space where A annihilates the vacuum. And only after doing that, then I can construct the classical theory. Now, if you want to know what the classical theory looks like, it's the question a comment I made to Alex a moment ago, Vikman. It looks like the classical action of Ostrogorsky, but continued into the complex plane, so that where I said for Alex, the y becomes Iy. So what it is, it continues into a complex version of the fourth order theory, not into the real one. The difficulties of Ostrogorsky only occur because you're working with real coordinates and real momentum. And the example we saw with Alex Vikman a few moments ago, which I commented on, was that if you chose to make the one of the coordinates y, in his case, anti-Hermitian, but kept the other one Hermitian, then the theory becomes bounded from below. Because the minus x squared, the minus y squared becomes, the minus py squared plus y squared becomes plus py squared plus y squared.
Okay, but so the field equation that you would obtain by variating the action for the Vial square are not the real field, they are not the classical field equations you're solving.
They're the classical equations, but continued into the complex classical plane. Another way to say that is the following. If you agree with me that I have to continue the quantum theory into the complex plane, and why do I do that? Because wave functions are not normalizable. And so I make them normalizable by going into the complex plane. In the complex plane, you could have asked me, well, is there a canonical prescription for that? And the answer is yes. You continue the Poisson bracket into the complex plane because it's a canonical transformation for Poisson brackets. It's a symplectic transformation. Now, usually in ordinary classical mechanics, the Poisson bracket algebra admits of a similarity of a symplectic transformation into the complex plane. It's a symmetry of classical mechanics. But we don't care to do that because we don't gain anything. When would you gain something if you had to continue into another domain in the complex plane where the theory suddenly becomes stable? In other words, the path integral for the Ostrogrodsky with real coordinates and momenta, that path integral doesn't exist. It blows up, it diverges. But if you continue the measure into the complex plane, you'll find a region in the measure, which is called a Stokes wedge, in which that path integral then does exist. And then in that Stokes wedge, you can quantize by identifying Poisson brackets with h bar times commutators.
Okay, I mean, I cannot say that I fully understood. Maybe I should think a bit more.
Okay, yes.
I'm not sure I totally agree, but I need to think a bit. But maybe I will just ask one last question, and then maybe.
Guys, I'm sorry, I have to go now. It's getting a bit late, and I have to attend some other stuff. So, yeah, thanks a lot.
Yes, bye-bye. Bye-bye.
Bye-bye.
Thank you very much. So my last question is, let's suppose we just consider a standard scalar field, two derivative with some interaction term, which is not a ghost. And now from your talk, we've learned that basically we can define inner products at least in two different ways. First, one way would be just to define the bra as a complex conjugate, like Hermitian of the ket. And the other one would be to use basically CPT or PT, depending on what we have. So let's suppose we define our theory in these two different ways. So we describe two different theories because we are defining two different inner products. Okay.
Yes.
How can you distinguish these two approaches in terms of prediction? Can you get different?
Yes. Yeah, I mean, okay. The statement is the following. The general rule is always the CPT conjugate. Now, in most theories in which you work, that just happens to agree with the Hermitian conjugate. Now, you know that time reversal is antilinear. So you know that the CPT transformation is antilinear. We don't always say this, but Hermitian conjugation is also antilinear because it changes H to H star, not H to H. So both of them are antilinear transformations. In every theory that we meet, which is second order, the two are the same. And the reason that they're the same is if you take any Lorentz scalar interaction, like psi bar psi, the Hermitian conjugation and the CPT conjugation leave psi bar psi invariant. In fact, Pauli noted this, and he called this strong reflection, because people were looking at CP, and he said, well, CPT will actually leave a Lorentz scalar function invariant. So for most theories, you never care about CPT. I mean, that's the CPT theorem. You just get it for free, so to speak. However, for these higher derivative theories, you do have to care. And then you don't have to give up anything that you already know if you use the CPT norm instead of the Hermitian norm. However, let's see where you go wrong. You calculate vacuum A dagger vacuum, and you find that it comes out negative. That's the ghost problem. Now, that's not possible because vacuum A is the conjugate of A dagger vacuum. And therefore that norm must be positive definite. And yet you found that it's negative. All that is telling you is that the dagger symbol doesn't mean Hermitian conjugate. It's telling you, you can't simply say Hermitian conjugate because you have to define a basis on which an operator acts in order to determine if it's Hermitian. I can tell you if an operator is CPT invariant. I can't tell you that an operator is Hermitian because I don't know what Hermitian means unless I have a basis. So you find a contradiction if you were to say a priori, I think something's Hermitian. In other words, let me say it in a different way. If I give you a Hamiltonian, you will say p squared plus x squared is Hermitian. Mm-hmm. But that's a meaningless statement. The statement is, when you construct the eigenstates of the Hamiltonian and the Hamiltonian acts on them, you can integrate by parts and throw away surface terms. But you can't tell that by just looking. You can't tell if a Hamiltonian is how it behaves until you define the states on which it acts. However, you can tell if a Hamiltonian has a symmetry, because that's a property of the individual terms. It's not a property of the states, it's a property of the operators. Whereas hermiticity is a property of the states. And so the main result that Carl and I have realized is hermiticity, which is a property of the states, works provided you act only on normalizable wave functions, because then you can integrate by parts. But you don't know if the wave function is normalizable until you solve the theory. You see?
Okay, yes. I will think a bit more about that, but thank you for the answer.
Yes, I mean, that's the, let me say this. I wrote a paper in Journal of Physics A about 3 or 4 years ago called Antilinearity as the Guiding Principle for Quantum Theory. And in other words, antilinearity, not hermiticity. And I go through all of this and discuss what we know. Now, when we write a commutator that xp is IH bar, it has no content until we say what the operators act on. And for that, you need good test functions. And so you look to see, do you have good test functions? You may have, you may not have. And you don't know that a priori.
Thank you.
And it's, okay. You must realize this took me an awful long time to comprehend, because it's totally unrelated, it's totally opposite to not only what I learned, but also how I've been teaching quantum theory. I myself.
Hi, Philip. Can I ask a very short question?
Of course.
Yeah. So, well, actually, a lot of questions Luke asked, which I want to ask. So, thanks for the detailed explanation. So, in your talk, you showed the conformal gravity, and when you solve the ghost problem, you're basically talking about propagator in Minkowski. So, my question is about curved spacetime, quantization in curved spacetime, and how do you solve ghost problem in curved spacetime.
Ah, okay.
How do you quantize gravity in curved spacetime? So
okay. The case that I've treated in the literature is quantization around flat.
Yeah.
But it's still quantum.
Yeah.
Okay. I've not worked through quantization about a curved background.
Okay.
However, my task was a very simple one. It was claimed that quantization around flat had negative norm states.
Okay.
Therefore, that was the thing I had to diffuse. Quantizing around a curved background is not easy in standard gravity.
Mm-hmm.
So the answer is I can't really tell you that. I can't really answer that. But if you quantize around flat and then you have a power series, the power series, when you sum it, will give you a curved Ricci tensor.
Well, I have. Well, it's a bit difficult to explicitly tell you what some example. Suppose you have a theory which is very good, no ghosts in flat spacetime, but ghosts appear in curved spacetime. If you have,
is that yes? You're asking me. The answer is, I suppose it's possible.
Yes, and then
you could have asked me. You could have asked me a different question. You could have asked me, the graviton is massless when you quantize around flat space-time.
Yes,
is it massless if you quantize around a curved space?
Yeah.
I don't see any reason for that, but on the other hand, since I haven't done a calculation, I can't give you an answer.
Okay, thank you.
But I've done a little bit more than that. Maybe I can give you some sort of an answer. Carl and I did not show that there was no ghost by getting rid of the ghost. What we showed was that the reasoning which made you think there was a ghost is incorrect.
Yeah, this I understand.
Yes, so if you have some reason for why there should be a ghost in the curved space case, we'll examine it and see whether it's valid.
Maybe I can tell you an example, but not now. It may take longer time. So, yeah.
Just a second, sorry.
Yeah.
Okay, so just a quick thing. Since there are Manuel and Ilya who are about to leave, are there any last moment questions for them? Yes.
I remember there were during the morning session.
We can discuss tomorrow also.
Yes. Yes, but I can ask.
Like the people here can ask.
So those Alexander Vikman.
Yeah, he left.
Okay.
Yeah, so the final thing that's left to do, I would say, is to give the word to Benjamin, who had a last, very last comment or question.
Yeah, I just wanted to pick up the discussion of the widespread gravity around flat space-time. So my fear with that theory is that you cannot define a graviton propagator because you have this extra conformal symmetry, which means that the conformal part of your propagator would diverge because the 2-point function in that sector vanishes. Have you thought about that at all, or yeah, can you comment on that, Philip?
Well, yeah. Well, since I've constructed a non-trivial propagator, why would you say the 2-point function vanishes?
No, so the TT part, so the transverse traces part, the spin 2 part does not vanish, but the part which relates to the conformal mode vanishes, right? Because the action is conformal. So
okay. I think I better answer your question differently. The 1/k⁴ propagator doesn't have the conventional spectrum because I'm working in a non-diagonalizable Hamiltonian.
Yes.
And so the whole notion of how you do things changes, but the 1/k⁴ I can use off shell. And that's the propagator, the 1/k⁴. And I use that off shell. But I can't, when I go on shell, I get I don't get the usual graviton picture. So there's a complete break between the off-shell propagator and the on-shell states.
Yeah. Okay. Thank you.
Yes. Is somebody here who asked me about R squared plus R? I think it was Luca.
Yeah, Luca asked.
Okay, Luca. R, the Ricci, we agreed before, the Ricci scalar changes sign if you let the metric go to I times the metric.
Yeah, seems so.
So, but the theory that we looked at would therefore have become R squared plus I R squared. R squared plus IR in that case. However, that's the one that we've shown is not unitary. It is unitary. Now, from my perspective, I'm not worried because I never have a linear term.
Yes,
but the question that's asked, that Alberto commented on, I still have to go through. I have to go through all the steps and see where the eyes go.
But so if you have Einstein-Hilbert term, this is problematic, right?
I'm not. I didn't want to say it was. I have to do the calculation because I don't continue everything into the complex plane.
Okay. Okay.
You see. I mean, that's what Alberto reminded us. I only continue half of the modes. Now, the whole story on fourth order oscillator, long ago, Pauli did mention that you could resolve the ghost problem by having pure imaginary coordinates. But that doesn't work in the fourth order case because only half of them become pure imaginary and not everyone. And that's why I think that's why it took so long to find. Because you think, okay, I'll continue into the complex plane, you'd immediately continue everything. But you don't. And that's why it's very hard. That's why it's very surprising.
Okay, for sure we'll come back to you by mail because I will maybe think a bit more about this. Okay.
Yeah, absolutely. Listen, just we can chat anytime.
Thank you.
I mean, it shouldn't surprise you, but I spend an awful lot of time at home now.
Okay. Okay. I think it's a great moment to end this very interesting discussion session. So thanks to everyone who's still here. Of course, many people have to leave, but yeah, I think all in all, it was very successful. Thank you, Philip, for these last comments. Thanks, everyone.
Thank you.
See you
now, just let me just mention that tomorrow you've only got a morning session.
Yes.
Yeah, that's going to put me under. That's going to be quite challenging for me.
Oh, I see. No. So basically, tomorrow we start 30 minutes before.
I know you're starting even earlier. Yes.
Yeah.
I hope to join you before the session finishes.
But it lasts a bit longer in the end. So for sure, maybe if you wake up around 7, maybe you can join. Well, if you cannot, it was a pleasure to have you with us.
Well, thank you.
Online. But I guess we will see you also tomorrow. So
no, I hope to come tomorrow. Yes.
Yeah. So, did you want to say something? No, just we will meet again. So tomorrow at 10 a.m. Central European time. Okay.
Yeah. Bye bye.
Thank you for sharing. My pleasure. Bye bye. Bye. See you.
So see you tomorrow, guys.